The sun has just committed a terrifying act. A massive aperture tore open across its surface, unleashing a torrent of plasma directly towards Earth. Simultaneously, the interstellar visitor, Comet 3I Atlas, vanished from the view of every telescope. And then, our planet, Mother Earth, experienced seismic tremors. Now, the foremost question on everyone's mind is, what exactly transpired? Was it annihilated, or has it undergone a transformation? And what might it resemble, if indeed it reappears at all? As one celestial wanderer recedes from view, another emerges into prominence. Comet Lemmon, an ancient icy remnant predating civilization itself, is now charting a rapid course across our night sky. We'll explain why the forthcoming 2 weeks are of paramount importance. Meanwhile, in China, physicists have achieved a breakthrough that sounds like pure science fiction. A communication network so secure it's unhackable, yet it functions as an absolute informant. And don't you dare blink, because before we conclude, we'll reveal the cosmic rendezvous you absolutely cannot afford to miss, including one that no one is discussing, but perhaps should be. If these enigmas have you on edge, as they have me, don't just passively observe, take action. Hit that like button, smash the subscribe icon, and remain tuned in as these narratives unfold in real time. Leave a comment detailing your location, the current time there, and be candid. Do you genuinely believe we're being privy to the complete truth regarding these world-altering discoveries? And if you're inclined to help this community flourish, please share this video on X, Facebook, Reddit, or even within your group chats. Every share, every comment, every click serves as fuel for our pursuit. You are the reason we can continue to chase these stories. Therefore, we extend our gratitude for standing with us in this quest. Part 1. The Disappearance. The sun just did something terrifying. October of the year 2025 arrived with a cosmic alarm bell that most individuals never perceived. Scientists intently observing our star watched with increasing apprehension as a colossal trans-equatorial coronal hole ripped open across the solar surface. It was a fissure in the sun's magnetic field, resembling a wound bleeding invisible energy into the vastness of space. This was far beyond typical solar activity, the kind that might produce spectacular auroras or perhaps cause minor disruptions to satellite signals. The hole was immense, extending across regions in both the northern and southern solar hemispheres concurrently. Such a configuration is a rare occurrence, and its implications are only beginning to be comprehended. The solar wind that emanated from this breach in the sun's magnetic shielding accelerated to speeds of 700 kilometers per second. To grasp this magnitude, imagine a hurricane where every single particle of air is moving at a velocity approaching 1.5 million miles per hour. The stream of charged particles, protons and electrons stripped from their atomic bonds, hurtled towards Earth like a cosmic fire hose aimed directly at our planet's protective magnetic field. The alignment was perfect, almost suspiciously so. The magnetic polarity of the solar wind precisely matched Earth's field orientation, creating the ideal configuration for maximum coupling, allowing for the strongest possible transfer of energy from the sun's outburst into our planetary magnetosphere. Geoscientists urgently worked to forecast the potential impacts. Power grid operators received immediate warnings. Satellite controllers prepared for potential malfunctions. Aurora enthusiasts, anticipating a celestial spectacle, packed their equipment and ventured northward, fully aware that such a powerful solar assault would paint the sky with colors that defy description. But something else occurred at that exact juncture, something that would elevate this solar event from a routine space weather incident to a profound cosmic enigma. Comet 3I Atlas, the second confirmed interstellar visitor ever detected within our solar system, inexplicably vanished behind the Sun. One moment, it was discernible, a faint speck of light traversing an orbit originating from another star system, carrying ice and rock formed in alien nebulae around a sun we would never behold. The next instant, it disappeared into the solar glare, completely obscured by the overwhelming brilliance of our star, rendering it invisible to every telescope on Earth and in orbit. The synchronicity of these events was impossible to disregard. Earth's magnetic field was being battered by the most potent solar wind in months, and concurrently, our sole accessible interstellar messenger went dark behind the very source of that onslaught. Scientists, by nature, are cautious individuals, trained to avoid premature conclusions and conditioned to adhere to the mantra that correlation does not imply causation. They chose their words with extreme care when reporters inquired if these disparate events could be interconnected. Then, the earthquakes began. Multiple magnitude 7 earthquakes struck various regions of Earth within hours of the solar wind's arrival. Seismometers registered the violent oscillations, the abrupt release of tectonic energy that had been accumulating for years, perhaps even decades, within the strained rock beneath our feet. Statistically speaking, these tremors were not entirely unexpected. Earth experiences approximately 15 magnitude 7 earthquakes annually on average. However, the occurrence of several in close temporal proximity to a significant solar event and the disappearance of an interstellar comet undeniably triggered something within humanity's inherent pattern recognition systems, that ancient part of our brains wired to seek connections and impose meaning upon coincidence. Could the sun's magnetic bombardment of Earth have somehow instigated seismic activity? The prevailing scientific consensus vehemently rejects this notion, stating that it fundamentally contradicts the principles of earthquake physics. Tectonic plates, it is argued, are indifferent to magnetic fields or solar winds. They shift and fracture according to the immutable laws of rock mechanics and accumulated strain energy. Nevertheless, dissenting voices exist, researchers operating at the fringes of geophysics who highlight statistical anomalies in earthquake timing during solar maxima. They propose hypothetical mechanisms involving ionospheric coupling or subtle alterations in Earth's rotational speed. While these unconventional ideas have yet to gain substantial traction within peer-reviewed literature, they circulate in the hushed corridors of academic conferences and within the bustling digital forums of the Internet. These are whispered possibilities, scenarios that mainstream science has not yet definitively refuted to everyone's complete satisfaction. The comet, however, is where the most profound mystery resides. 3I Atlas rightly earned its designation as the third confirmed interstellar object detected traversing our solar system. The first was Oumuamua, encountered in 2017, a bizarre, elongated object that tumbled through the inner solar system, exhibiting accelerations that defied explanation through conventional comet outgassing. The second was 2I Borisov in 2019, which presented a more familiar appearance and behavior, a reassuring sphere of ice and dust following predictable physical principles. 3I Atlas was discovered in the year 2025, tracked as it descended towards the Sun on a hyperbolic trajectory, moving with a velocity too great to be gravitationally bound to our star. It was unequivocally a visitor, merely passing through on its return journey to interstellar space. Such objects are of immeasurable value to the scientific community. They represent our sole available samples of material originating from other stellar systems, at least until we develop the technology to dispatch probes to neighboring stars and retrieve physical specimens, a feat that will not materialize within any of our lifetimes. Every single photon of light we collect from an interstellar comet carries vital information about its chemistry, the composition of protoplanetary disks around distant suns, and whether the processes that shaped our own solar system are universal phenomena or unique occurrences. When 3I Atlas vanished behind the Sun, our capacity to gather this crucial data was, at least temporarily, lost. The question now haunting astronomers is far simpler, yet more disquieting, than any speculation regarding solar winds or earthquakes. When 3I Atlas re-emerges from behind the Sun, assuming it does re-emerge, will we even recognize what appears? Did our Sun just consume our interstellar visitor? Could the intense heat, radiation, and magnetic turbulence in close proximity to our star have fundamentally reshaped it, torn it asunder, or vaporized it entirely? We are on the precipice of discovering the answer, and the revelation may well overturn everything we currently understand about these alien celestial wanderers. Part 2. The Traveler We Lost. The narrative of 3I Atlas, like most comet discoveries, begins with an exercise in patience. Automated telescopes diligently scan the night sky, meticulously searching for any anomaly that moves against the static backdrop of stars. The Atlas Survey, an acronym for the Asteroid Terrestrial Impact Last Alert System, comprises 4 robotic telescopes strategically positioned around the globe, primarily tasked with detecting asteroids that could pose a collision risk to Earth. However, these telescopes possess an indiscriminate gaze. They capture everything that exhibits motion, including comets. And during the early months of the year 2025, they captured something truly extraordinary. The object initially appeared as a faint streak within images obtained from the Hawaiian observatories. Subsequent observations from other facilities confirmed its movement and, indeed, its rapid velocity. Trajectory calculations revealed the unmistakable hallmark of a hyperbolic orbit, an eccentricity exceeding 1, signifying that this object was not gravitationally tethered to the Sun. It originated from an external source, and following its close passage by our star, it was destined to depart, heading back into the vast cosmic ocean between stars. Its orbital energy was inconsistent with that of a body native to our solar system. This was, without question, interstellar. The astronomical community reacted with swift mobilization. Telescope time, an inherently scarce resource and a commodity typically booked months in advance, was suddenly made available. Spectroscopy, the meticulous analysis of light reflected or emitted by the comet, became the paramount objective. What precisely was this entity composed of? Did it contain the same amalgamation of water ice, carbon dioxide ice, and organic molecules characteristic of comets born within our solar system? Or would its composition betray an alien chemistry, elemental ratios that pointed towards formation conditions around a fundamentally different type of star? Early data yielded perplexing results. The luminosity of 3I Atlas did not behave in the manner astronomers had anticipated. Typically, comets brighten as they approach the Sun, their luminosity following a predictable curve linked to the increasing sublimation of ice. As solar heating intensifies, water ice begins to sublimate, transitioning directly from a solid to a gaseous state when sunlight warms the surface to approximately 200 Kelvin. Other volatile substances, such as carbon monoxide and carbon dioxide, sublimate at even lower temperatures, triggering activity at considerably greater distances from the Sun. The brightness curve exhibited by 3I Atlas presented periods of flattening, where the comet's luminosity did not increase as predicted by models, followed by abrupt surges in brightness that suggested discrete outbursts of dust or gas. The coma, the diffuse envelope of gas and dust encircling the nucleus, appeared unusually faint in certain observations. The production of dust seemed to be lower than expected for a comet of its inferred size. Some researchers posited that the nucleus might possess an unusually high density, with a greater proportion of rock to ice, which would account for its subdued activity. Others suggested the opposite, that the nucleus was exceptionally porous, akin to a rubble pile held together by weak gravitational forces, and that this structural characteristic was inducing the ice to sublimate in unpredictable bursts rather than a steady, continuous flow. Then there were the non-gravitational forces. Comets do not adhere to purely Keplerian orbits, which are dictated solely by the Sun's gravitational influence. As ice sublimates from the nucleus, it generates jets of gas that act as miniature rocket engines, subtly deflecting the comet from its predicted path. These non-gravitational accelerations are minor but measurable, and they introduce an element of uncertainty into precise predictions of the comet's location at any given moment. In the case of 3I Atlas, these orbital perturbations proved particularly challenging to model. The calculations of its orbit underwent continuous refinement, the margins of error persistently shifted, and astronomers grew increasingly uncertain about the exact timing and location of the comet's reappearance from behind the Sun. Some observations hinted at potential fragmentation occurring prior to its disappearance. Comet nuclei are inherently fragile entities, loosely bound collections of ice and rock that can fracture under thermal stress or tidal forces. When a comet fragments, it frequently generates a trail of smaller fragments following similar orbital paths, sometimes visible as multiple discernible condensations within the coma. Imaging of 3I Atlas revealed possible asymmetries, elongated shapes that might indicate the nucleus was beginning to disintegrate. If the comet was already fracturing before it vanished, the subsequent questions become even more pressing. What might emerge from the solar glare? Perhaps not a singular entity, but a dispersed stream of debris, or conceivably, nothing at all, should the fragments diminish to an undetectable size. The inevitable point of comparison was with previous interstellar visitors. Oumuamua, the first detected interstellar object, was never definitively confirmed to be a comet. It displayed no discernible coma, no dust tail, and no features that would unequivocally classify it as an icy body. Yet, it accelerated away from the Sun in a manner that could not be attributed to gravitational forces alone. The most plausible explanation remained comet outgassing, but of a volatile substance more exotic than water, possibly carbon monoxide or molecular nitrogen, compounds that would sublimate without producing visible dust. The alternative hypotheses, ranging from light sails to alien spacecraft, captured the public imagination, but garnered scant support from scientists who prioritize empirical evidence over speculation. 2I Borisov, on the other hand, behaved more like a conventional comet, possessing a distinct coma and tail, along with brightness variations that aligned reasonably well with standard comet models. Its spectrum revealed the presence of water vapor and carbon monoxide, exhibiting chemistry akin to what is observed in solar system comets. This offered a degree of reassurance, suggesting that planetary formation around other stars follows similar principles and produces comparable celestial bodies. However, Borisov also exhibited signs of fragmentation in proximity to its perihelion, its closest approach to the Sun. Images captured what appeared to be a small fragment detaching from the main nucleus, a stark reminder that these interstellar travelers do not always survive their passage through the inner solar system intact. Now, 3i Atlas was following a comparable trajectory, diving towards the Sun, and we had lost visual contact at the most inopportune moment. The geometrical configuration of solar conjunction, wherein an object passes behind the Sun from Earth's perspective, creates an observational void that can persist for days or even weeks, contingent upon the object's trajectory and luminosity. For a faint comet that was already exhibiting unusual behavior, this void transforms into a black box, a period during which anything could transpire without our knowledge. The comet could be disintegrating. It could be undergoing a dramatic brightening. It could remain intact, simply obscured by the sun's intense glare. We would remain in ignorance until its emergence, if indeed it emerged. Models were employed in an attempt to predict the outcome based on assumed nuclear dimensions and compositions. If the nucleus was substantial and predominantly rocky, thermal models indicated it would likely survive with minimal mass loss. Conversely, if it was small and icy, the intense heat near perihelion could entirely vaporize it, leaving behind only a dispersing cloud of gas and dust. The uncertainty regarding the nucleus's size was immense, ranging from a few hundred meters to several kilometers, representing a tenfold or greater disparity. This inherent uncertainty propagated through every predictive model, transforming forecasts into mere conjecture. The phrase that astronomers repeatedly used was invisible interstellar traveler. Somewhere beyond the sun's blinding glare, concealed from every telescope humanity has ever constructed, an entity from another star system was either enduring or perishing, and we could do nothing but await and ponder what would materialize once the celestial geometry finally permitted observation once more. The period of waiting felt like an eternity compressed into mere days. Part 3. When solar wind encounters alien ice. The Sun is not a benevolent entity. We perceive it as our benign, life-sustaining star, the source of the warm light that renders Earth habitable. However, when observed up close, the Sun reveals itself as a violent, chaotic, incandescent sphere of plasma, where temperatures soar into the millions of degrees and magnetic fields twist into configurations that store energy like tightly wound springs. When these stored energies are abruptly released, the consequences can be catastrophic for any nearby object. The coronal hole that manifested in October of the year 2025 was precisely the kind of event that instills apprehension in solar physicists. Coronal holes represent regions where the sun's magnetic field lines diverge into space rather than looping back to the solar surface. These open field lines function as conduits for solar wind, enabling plasma to escape into the solar system at exceptionally high velocities. A typical solar wind speed hovers around 400 kilometers per second. The wind emanating from this particular coronal hole, however, was traveling at 700 kilometers per second, nearly double the usual rate, carrying significantly more momentum, energy, and a greater potential for disruption. When solar wind at such speeds interacts with a comet, the resulting encounter becomes both complex and tumultuous. Comets lack the magnetic shielding that Earth possesses. They do not have a magnetosphere to deflect the incoming charged particles. Instead, the solar wind directly impacts the coma, the diffuse cloud of gas and dust surrounding the comet's nucleus, initiating a cascade of unusual physical phenomena. The gas within the coma becomes ionized by the sun's ultraviolet radiation, creating a population of electrically charged molecules. These ions are responsive to magnetic fields, and the solar wind carries embedded magnetic field lines that drape themselves around the comet like a cape. The resultant structure is known as a magnetotail, formed by the interplay between the solar wind's magnetic field and the ionized gas originating from the comet. This tail can extend for millions of kilometers downstream, away from the sun, emitting a faint glow from ionized carbon monoxide and other molecular species. The tail is not a static formation. Turbulence within the solar wind causes it to undulate and flutter. Disconnection events can occur, wherein the tail completely detaches and a new one begins to form. These interactions are observable from Earth with appropriate instrumentation and provide valuable insights into both solar wind conditions and the comet's gas production rate. But what transpires when a comet encounters an exceptionally swift solar wind, while already subjected to intense solar heating in proximity to its perihelion? Historical records offer some terrifying precedents. Comet Ison, discovered in 2012 and anticipated to become spectacularly brilliant, disintegrated during its close passage by the Sun in 2013. Images captured by solar observing spacecraft depicted the comet entering the perihelion region as a luminous object and emerging as nothing more than a dispersing cloud of dust. The nucleus had apparently fractured completely, unable to withstand the combined thermal and tidal stresses. Comet Lovejoy, a sun grazer that passed within 140,000 kilometers of the solar surface in 2011, astonishingly survived despite predictions that it would be obliterated. Images revealed the comet's tail extending for millions of kilometers post-perihelion, sustained by massive gas production from its superheated nucleus. The survival of Lovejoy was an unexpected event and remains not entirely explained. Some confluence of its nuclear size, composition, and structural integrity enabled it to endure heating that should have rendered it entirely vaporized. 3I Atlas was not approaching the sun as closely as those extreme sun grazers, but it was entering the region where solar influence becomes paramount, and it was doing so during a period of unusually potent solar wind. The crucial question became whether the combined factors, thermal stress, radiative heating, solar wind pressure, and potential pre-existing fragmentation, would prove sufficient to destroy it. Certain researchers proposed more unconventional interaction scenarios. The electric comet model, advocated by a small contingent of plasma physicists, posits that comets develop electrical charges through their interaction with the solar wind, and that electrical forces, rather than solely thermal sublimation, drive cometary activity. Mainstream astronomy has not widely embraced this model, finding that conventional physics adequately explains observed phenomena without invoking electrical effects. However, proponents point to occurrences such as disconnection events in comet tails and rapid fluctuations in brightness as evidence that electrical processes play a significant role. This hypothesis extends further into speculative territory, with suggestions that powerful solar wind events could induce charge separations within a comet's coma, potentially leading, under specific circumstances, to explosive ruptures or trajectory deviations beyond those predictable from simple outgassing. The validation for these assertions is disputed. The theoretical underpinnings are insufficient, yet the concepts persist because they strive to account for phenomena that do not perfectly align with established models. When 3 Atlas vanished during a significant solar wind event, proponents of electric comet theories perceived this as potential corroboration of their hypotheses. Mainstream astrophysicists, however, viewed it as an unfortunate but ultimately incidental confluence of occurrences. What amplifies the uncertainty is our actual lack of knowledge regarding the composition of 3 Atlas. Spectroscopic examinations conducted prior to its disappearance were limited and did not yield a comprehensive inventory of its constituents. The celestial body could be predominantly water ice, akin to many comets within our solar system. Alternatively, it might be primarily carbon monoxide ice, which vaporizes at much lower temperatures, thereby enabling activity at greater distances from the Sun. It could also be rich in silicates and deficient in volatile compounds, more resembling an asteroid than a typical comet. Each distinct composition would react differently to solar heating and interactions with the solar wind. If the nucleus possesses extreme porosity, akin to aerogel, with a density barely exceeding that of the gas within the coma itself, thermal waves would penetrate deeply, heating subsurface ice and potentially causing the entire structure to fragment through a cascading sublimation process. Should the nucleus be shielded by an insulating layer of dust covering most of its surface, gas production would be confined to a few active regions, generating jets that could induce rotation or alter its spin in unpredictable ways. If the nucleus is a contact binary, comprising two lobes bound by weak gravitational forces, tidal stresses and thermal strain could cause it to fracture. In this context, the Sun effectively acts as a cosmic arbiter, a destructive agent that scrutinizes every object traversing the inner solar system. Interstellar comets, having originated in dissimilar environments and possibly possessing different structural characteristics compared to those within our solar system, might be especially susceptible, or conversely, they might be more resilient, having been formed under conditions that rendered them tougher. We will not ascertain this until we observe its reappearance. The comparison with comet Shoemaker-Levy 9 offers insight. That comet was fractured by tidal forces during a close pass by Jupiter in 1992, breaking into over 20 fragments that subsequently impacted the planet in a remarkable sequence of collisions. The tidal disintegration occurred because the gravitational gradient exerted by Jupiter across the comet's diameter surpassed the comet's own self-gravitational pull, literally tearing it asunder. The Sun's tidal forces are considerably weaker at the distance at which 3 Atlas passed. However, a comet already weakened by thermal stress or prior fragmentation could succumb to forces that a healthy nucleus would readily withstand. Did the Sun just unveil something alarming about celestial visitors from beyond our solar system? The resolution hinges on what we observe when the comet re-emerges from conjunction. If 3 Atlas reappears intact, continuing along its hyperbolic path with normal gas and dust emission, the solar wind event will become a mere footnote, a coincidental occurrence that fueled conjecture, but ultimately held no profound significance. If the comet has disintegrated or vanished, we are left with perplexing questions about whether objects originating from interstellar space are inherently more fragile than our models suggest, or if there is an aspect of their formation or internal structure that renders them vulnerable to solar assault in ways we had not anticipated. Part 4. The observation period commences. Astronomers are marking their calendars, verifying ephemerides, and devising observation strategies for the precise moment when 3 Atlas is expected to become visible once more. The timing is contingent upon several factors, including the comet's exact trajectory, which is subject to uncertainty due to non-gravitational influences, its luminosity, which may have undergone dramatic alterations, and the observational geometry, which dictates how far from the Sun the comet must be before telescopes can detect it against the celestial background. Current projections indicate that the comet should emerge from solar conjunction in late October or early November of 2025, achieving sufficient solar elongation, the angular distance from the Sun as viewed from Earth, to be observable with specialized instruments. Initial attempts at recovery will likely involve space-based observatories capable of obscuring the sun's intense light more effectively than terrestrial telescopes. The Solar and Heliospheric Observatory, for instance, is equipped with coronagraphs designed to generate artificial eclipses, facilitating observation of the region proximate to the Sun where comets frequently reside. STEREO, the Solar Terrestrial Relations Observatory, comprising 2 spacecraft in solar orbit, provides varied perspectives that might detect the comet sooner than Earthbound observations. The Parker Solar Probe, humanity's most daring approach to the Sun, follows an orbit that periodically brings it within Mercury's orbital path, traversing regions where solar wind speeds and temperatures reach extreme levels. Should the probe's trajectory have intersected with 3 Atlas during the conjunction period, its instruments might have recorded data about the comet under conditions inaccessible to any Earth-based telescope. However, the Parker probe's scientific objectives are focused on the solar corona and solar wind, not comets. And unless the comet happened to fall within the probe's narrow field of view at the opportune moment, we will have no data from that critical interval. Mission scientists have not reported any fortunate encounters, suggesting that the geometric alignment was not favorable, or that the comet was too faint for Parker's instruments to detect against the brilliant solar backdrop. What will the initial recovery images reveal? In the most optimistic scenario, the comet will appear as anticipated, perhaps slightly dimmer due to dust loss, but otherwise intact, exhibiting a discernible coma and tail indicative of active ice sublimation from the nucleus. The spectral signature would display familiar lines corresponding to water vapor, cyanogen, and carbon monoxide, the molecular fingerprints that confirm its cometary composition. The tail's length and structure would furnish insights into the rate of gas production and the prevailing solar wind conditions in the post-conjunction phase. Astronomers will measure its brightness, compare it to pre-conjunction values, and assess whether the comet experienced substantial mass loss during its closest solar proximity. In the most pessimistic scenario, nothing will be detected. The sky will remain devoid of the expected presence of 3 Atlas, suggesting complete disintegration. The nucleus may have fractured into fragments too small to be individually resolved, or may have entirely vaporized, leaving behind only a dispersed cloud of gas, too diffuse to be observed as a distinct entity. This outcome, while scientifically disappointing, is not without precedent. Numerous comets have vanished following close solar encounters, and their disappearance becomes a data point contributing to our understanding of cometary fragmentation dynamics. Between these 2 extremes lie a multitude of possibilities. The comet could return as multiple fragments, forming a series of condensations along its orbit, indicating that the nucleus had split, but the resultant pieces had survived. Such fragment streams are challenging to observe because each individual piece is fainter than the original nucleus, yet they offer valuable information regarding nuclear structure and the mechanics of breakup. If 3I Atlas reappears as fragments, analysts will meticulously measure the separation distances and velocities to reconstruct the timing and mechanism of the fragmentation event. Another potential outcome is dormancy. The comet might have depleted its near-surface volatile reserves during the close solar passage, leaving behind a desiccated crust that inhibits further sublimation until solar heating cracks this crust or erosion exposes fresh ice. Dormant comets resemble asteroids, exhibiting no coma or tail, merely a rocky surface reflecting sunlight. Should 3I Atlas enter a dormant state, our ability to study its gaseous composition will be curtailed, but we will gain valuable insights into surface processes and the formation of insulating mantles. The most compelling scenario involves an unexpected increase in brightness. Occasionally, Comets fragment in ways that expose fresh, volatile, rich material to solar radiation, triggering abrupt surges in gas production and luminosity. A fragmenting nucleus can create new active zones, thereby expanding the total sublimating surface area. If 3 Atlas undergoes fragmentation and simultaneously brightens, the comet that re-emerges could be even more spectacular than the one that vanished. However, in a fragmented state, it would likely fade rapidly as the smaller pieces exhaust their ice reserves. Spectroscopic analysis will be paramount. Observations conducted before conjunction revealed the typical signatures of water and potentially carbon monoxide, but a complete spectral inventory was never obtained. Post-conjunction spectroscopy might reveal species that were not previously detected, either because the comet was not producing them in significant quantities or because our observations were not focused on the appropriate wavelengths. Oxygen emission lines would indicate water sublimation. CN, cyanogen, points to carbon-nitrogen chemistry. Sodium and iron lines are sometimes observed in comets and can signify the exposure of metallic-rich material from the nucleus's interior. Amateur astronomers have a crucial role to play in the recovery endeavour. A globally distributed network of backyard telescopes provides continuous sky coverage that professional observatories, with their limited observation time and scheduled programs, cannot match. Should 3 Atlas brighten unexpectedly or fragment into widely dispersed pieces, amateur observers may be the first to notice. Crowdsourced astronomy has become increasingly vital as digital cameras and sophisticated software empower dedicated amateurs to produce observations that rival professional-grade data. A live cosmic enigma is unfolding in real time, and anyone equipped with a telescope and clear skies can participate. The comet could reappear at any moment, assuming it has survived. Alternatively, days, then weeks, might pass with no visible presence until astronomers reluctantly conclude that 3I Atlas is irrevocably lost, destroyed by the sun, having journeyed so far to visit. The uncertainty is simultaneously maddening and exhilarating. We have dispatched no probe to intercept the comet. We possess no means to actively search for it beyond directing our telescopes toward its predicted location and patiently waiting. All we can do is observe, contemplate, and prepare for whatever emerges from the sun's glare. The broader question continues to preoccupy the astronomical community. If the nucleus is gone, does 3 Atlas still exist? Or has it transformed into mere debris, a dispersed cloud of dust and gas that was once an interstellar comet, but no longer qualifies as a discrete object? Philosophically, this echoes the ship of Theseus paradox. If every plank of a wooden ship is replaced over time, does it remain the same vessel? If a comet fragments into 1,000 pieces, each following a nearly identical orbit and carrying material from the original nucleus, do they collectively still constitute the comet, or has the comet ceased to exist? There is no formal definition that definitively resolves this quandary. It is a matter of convention and practicality, and different researchers will offer varying responses depending on their perspectives. However, the question holds significance because 3 Atlas represents something precious and inimitable, a sample from another star system. And its loss feels like more than just the disappearance of an astronomical target. It feels like the severance of a connection to something vast and distant, a thread linking us to the wider galaxy that was snapped before we could fully comprehend what we possessed. Part 5. When coincidence morphs into conspiracy. Why does any of this hold importance beyond the confined domains of planetary science journals and astronomical conferences? Because humans are beings who inherently seek patterns, who evolved to discern meaning in correlations and to perceive connections even where none truly exist. The simultaneous occurrence of a major solar event, the vanishing of an interstellar comet, and multiple significant seismic events on Earth triggered every alarm within our collective subconscious, signaling that something profound is transpiring. The prevailing scientific consensus regarding the connection between solar activity and terrestrial earthquakes is unequivocal. Earthquakes are precipitated by plate tectonics, by the slow, inexorable movement of lithospheric plates riding atop the convecting mantle, and by the accumulation of strain energy within the crust that eventually overcomes the frictional resistance holding faults in place. Solar activity possesses no plausible mechanism to instigate this release. Magnetic fields do not exert influence over rock. Solar wind particles do not penetrate to Earth's surface. They are arrested by the magnetosphere and atmosphere. The thermal energy imparted by solar radiation is negligible in comparison to Earth's internal heat. Every analysis of earthquake catalogues, when seeking correlations with solar cycles or individual solar events, has yielded no results beyond what would be statistically anticipated by chance. Nevertheless, correlations continue to emerge in datasets, presenting tantalizing patterns that fall just short of statistical significance, yet persistently refuse to dissipate entirely. Some researchers, operating at the fringes of scientific respectability, persist in exploring potential mechanisms. Could ionospheric disturbances induced by solar activity influence the electrical properties of fault zones? Could subtle shifts in Earth's rotational rate or magnetic field orientation, driven by solar wind momentum transfer, modulate tectonic stress at levels too minute to be directly measured, yet sufficient to trigger a fault already nearing failure? Could there be magneto-hydrodynamic coupling between the ionosphere and conductive layers within the crust that transmits energy in ways yet to be fully comprehended? These hypotheses face immense skepticism because extraordinary assertions demand extraordinary substantiation, and the available evidence remains circumstantial at best. However, the human mind does not operate solely on statistical significance thresholds. It functions through narrative, through stories that weave disparate events into coherent wholes. When the sun unleashes its power, earthquakes strike, and a comet disappears. All within the same news cycle, the narrative constructs itself, even if the underlying physics does not support it. The interstellar origin of 3A Atlas introduces an additional dimension of enigma and speculation. These objects emanate from beyond our solar system, from environments we can scarcely imagine, formed from materials whose composition and isotopic ratios may diverge from solar system norms. They are, in the most precise sense of the word, literally alien, and humanity has invariably projected its hopes and fears onto the alien and the unknown. When Oumuamua exhibited acceleration that could not be immediately attributed to standard cometary outgassing, speculation arose regarding its artificial origin, suggesting reconnaissance by alien probes or technologies surpassing our comprehension. The most straightforward explanation remained natural processes, yet the alien probe hypothesis captured public imagination because it satisfied narrative needs that dry scientific papers on carbon monoxide sublimation could never fulfill. The disappearance of 3 Atlas during a solar storm invites similar conjecture. Did the comet harbor something or encode information that rendered it a target? Are we witnessing a cosmic quarantine protocol, with the sun eliminating potential threats from interstellar space before they can infiltrate the inner solar system? The scientific implausibility of these notions does not diminish their psychological allure. We desire the universe to hold mysteries deeper than orbital mechanics and spectroscopy. We seek hidden meanings behind celestial alignments. We wish for comets to be more than mere icy debris. We desire them to be messengers, carriers of information, life, or purpose. The hypothesis of panspermia, the concept that life disseminates throughout the cosmos aboard comets and asteroids, lends a scientific veneer to these aspirations. If comets delivered the organic precursors that initiated life on Earth during the period of intense bombardment billions of years ago, then every comet becomes a potential seed carrier, and interstellar comets become exceptionally valuable because they might transport chemistry from biospheres orbiting other stars. The obliteration of 3 Atlas, if that is indeed what transpired, would then represent the destruction of a biological sample, a library consumed before its contents could be deciphered. More esoteric possibilities circulate within fringe communities. Proponents of the electric universe theory perceive the sun's interaction with the comet as evidence of plasma physics, which they contend is ignored by mainstream science. They point to the comet's unusual fluctuations in brightness, the intense solar wind, and disconnection events observed in other cometary narratives, arguing that these phenomena necessitate electrical rather than gravitational and thermal explanations. The mathematical frameworks of their models rarely withstand rigorous scrutiny. Predictions frequently fail to align with observations, yet the intuitive appeal of electricity as a universal force, coupled with the visual drama of lightning and sparks, imbues electric universe ideas with a persistence that transcends their scientific deficiencies. Conspiracies inevitably arise. Are space agencies withholding data from the Parker Solar Probe's close solar passes? Did instruments capture images or spectra of 3I Atlas during the conjunction period that officials deliberately concealed? What motive would impel such secrecy? Perhaps the comet displayed behavior that defied explanation, challenged fundamental assumptions, and alarmed those who grasped the implications. Perhaps it fragmented in a manner inconsistent with natural processes, or emitted signals, or altered its trajectory in ways that suggested deliberate control. These scenarios are exceedingly improbable, bordering on impossible. However, in minds predisposed to distrust official narratives, the absence of evidence becomes construed as evidence of conspiracy. The psychological function of conspiracy theories is well documented. They provide a sense of control, or the illusion thereof, when confronted with random and chaotic events. They supplant a universe governed by meaningless coincidence with one characterized by hidden order and purpose, even if that purpose is malevolent. It is preferable to believe in conspiracies than to accept that earthquakes occur randomly, that comets disintegrate without discernible reason, and that we are but tiny sparks of consciousness on a fragile world hurtling through an indifferent cosmos. The narrative of concealed knowledge and suppressed truth is more emotionally gratifying than the narrative of patient scientific investigation, slowly converging on tentative conclusions. Yet, here is the crucial point. Sometimes, the universe does align in ways that defy probability. Sometimes, coincidences are too perfect to dismiss, even when causality cannot be definitively established. The October 2025 convergence of events, the solar storm, the comet's disappearance, and the earthquakes, may indeed be precisely that. A coincidence so improbable it warrants our attention, even if, ultimately, it signifies nothing. Or it could represent the nascent indication of connections we have yet to comprehend, subtle couplings between geophysical systems and space weather that operate at levels below our current detection thresholds. Scientific progress is driven by the investigation of anomalies, not by their dismissal. The researchers examining solar earthquake correlations are engaged in legitimate, albeit speculative, scientific inquiry. They will likely find nothing conclusive, but the pursuit itself holds intrinsic value. When 3 Atlas emerges from behind the Sun, should it emerge, we may not recognize it. The comet that entered that region might not be the same comet that subsequently exits. And when astronomers publish their analyses of their observations, when they present explanations grounded in physics, chemistry, and orbital mechanics, some individuals will accept those explanations and move forward. Others will continue to search for hidden meanings, for connections between the comet, the earthquakes, and the solar storm that transcend material causation. Both responses are inherently human. Both reflect deep-seated needs to comprehend our place in a cosmos that offers more questions than answers. The Sun performed a terrifying act. A comet vanished, the Earth trembled, and whatever underlying truth exists, we are left with a profound sense of wonder and unease in equal measure. Part 6. The Comet We Can See. While Comet 3 Atlas remains hidden from view behind the Sun, another celestial traveller is putting on a spectacle, provided you know when and where to gaze. This comet, C2025A6, christened Lemmon by its discoverers at the Mount Lemmon Observatory in Arizona, is nearing its closest approach to the Sun. Its luminosity is anticipated to reach levels visible with binoculars, small telescopes, and potentially even the unaided eye under exceptionally dark skies, far from the glare of artificial lights. The forthcoming 2 weeks represent the prime opportunity for observation. Lemmon's perihelion, its point of closest proximity to the Sun, is slated for mid-November of 2025. However, its orbital trajectory will render it most prominent from Earth slightly before this date, when it's still sufficiently distant from the Sun's overwhelming brightness to be observed comfortably. Currently, the comet graces the pre-dawn eastern horizon, appearing several hours before sunrise. It emits a soft, hazy glow, characteristic of an active comet possessing a well-formed coma and possibly a nascent tail. Forecasts suggest Lemmon's magnitude will hover between 4 and 5, placing it at the very edge of naked-eye visibility. Under optimal conditions, the human eye can typically discern objects down to magnitude 6. A magnitude 4 object should be readily apparent away from urban illumination, though precisely locating it without optical aid necessitates prior knowledge of its precise position. The comet is presently traversing the constellation Cancer, progressing eastward against the backdrop of fixed stars. Online resources offer star charts detailing its path in relation to familiar stellar groupings. Observing comets demands both patience and darkness. Unlike planets, which appear as distinct points or disks, comets are diffuse entities, their light spread across a considerable area. This dispersed nature makes them far more susceptible to light pollution and atmospheric disturbances than compact celestial bodies of comparable overall brightness. A magnitude 4 comet will effectively vanish in brightly lit suburban skies, where magnitude 4 stars remain easily visible. Success hinges on venturing away from metropolitan zones to locations where the Milky Way arches overhead, and the profound darkness of the night sky permits the human eye to perceive extended objects of low surface brightness. Binoculars are the ideal tool for comet observation. They offer sufficient magnification to concentrate the comet's light while maintaining a broad field of view, which facilitates both the initial discovery and continuous tracking of the object. 7 by 50 binoculars, a common size among amateur astronomers and nature enthusiasts, are particularly well suited for this purpose. Mounting them on a tripod, if feasible, will mitigate hand tremor and allow for extended viewing periods without fatigue. The comet will manifest as a small, nebulous smudge, clearly not stellar in appearance, and may exhibit a subtle greenish hue attributed to the emission of diatomic carbon molecules within its coma. Telescopes can reveal finer details, showcasing the coma's internal structure, any jets or plumes of material emanating from active regions on the nucleus, and the tail, should it have developed sufficiently. However, higher magnifications significantly narrow the field of view, making the comet more challenging to locate initially and to keep centered as Earth's rotation carries it across the sky. Many seasoned comet watchers favor binoculars for their aesthetic qualities. The expansive field of view presents the comet within the context of the star-strewn sky and the Milky Way, emphasizing its transient nature as a visitor navigating the more permanent celestial panorama. Early observations of Lemmon have revealed aspects that simultaneously excite and concern comet scientists. Its observed brightness has not perfectly aligned with predictive models. Comets are notoriously unpredictable, their luminosity contingent upon factors that are difficult to quantify directly, such as nucleus size, composition, rotational state, surface characteristics, and the ratio of dust to gas. Models rely on statistical assumptions derived from other comets, but individual comets often deviate from average behavior. Lemmon has exhibited periods of unexpectedly rapid brightening, interspersed with plateaus where its luminosity remained relatively constant despite its decreasing proximity to the Sun. These discrepancies could signify several phenomena: outburst activity, wherein the sudden exposure of fresh volatile materials triggers a temporary surge in gas and dust production, can lead to rapid brightening. Rotation of the nucleus, exposing different hemispheres to sunlight if one is more active than the other, can induce periodic luminosity variations. Alternatively, and more ominously, these deviations might foreshadow the nascent stages of fragmentation, where the nucleus begins to fracture under thermal or tidal stresses. Fragmentation represents the hidden peril that perpetually shadows every comet prediction. A comet might appear to be brightening normally, adhering to its predicted trajectory toward perihelion, seemingly healthy in every regard, only to suddenly begin disintegrating. This process can occur with alarming rapidity or a more gradual progression. Sometimes, a substantial fragment detaches, forming a distinct condensation observable near the main nucleus. In other instances, the entire nucleus disintegrates into a diffuse cloud of minute fragments, individually too faint to detect, but collectively capable of causing a dramatic increase in overall brightness as their combined surface area drives heightened sublimation. The physics governing fragmentation involves mechanical strength, thermal stress, and rotational dynamics. Comet nuclei are inherently weak structures, resembling compacted snow rather than solid rock, held together primarily by their own weak gravitational pull, augmented by the tensile strength of ice and potentially organic tars. When solar radiation heats one side of the nucleus, thermal expansion generates stress. If the nucleus is rotating, centrifugal forces add mechanical stress, and ejected jets can induce torques that accelerate the nucleus's rotation. At a certain threshold, the accumulated stress surpasses the material's inherent strength, causing cracks to propagate and the nucleus to split. Lemmon sublimation processes introduce an additional layer of complexity. The comet appears to be driven by the sublimation of carbon monoxide or carbon dioxide as much as, or even more so than, water. These molecules are more volatile than water, meaning they transition from solid to gas at lower temperatures and greater distances from the Sun. A comet primarily driven by carbon monoxide can remain active far beyond the snow line, the region where water ice remains frozen, producing a coma and tail while still in the outer solar system. As the comet approaches perihelion and temperatures escalate, water sublimation eventually predominates, often leading to a shift in activity patterns and brightness behavior. The interaction of the tail with the solar wind offers another avenue for observation. Lemmon's ion tail, if one develops, will point directly away from the sun, propelled by the solar wind, much like a windsock. The dust tail, however, follows a curved trajectory. Its particles are propelled by solar radiation pressure, but retain the orbital momentum they possessed when released from the nucleus. These two distinct tail types, ion and dust, often separate into visually discernible structures in photographs. The ion tail typically appears bluish, owing to the emission of carbon monoxide ions, and presents as straight, occasionally featuring streamers and knots influenced by irregularities in the solar wind's magnetic field. The dust tail, conversely, is yellowish-white from reflected sunlight, broader and more diffuse, curving gently away from the nucleus. Comparing Lemmon to 3 Atlas highlights fundamental differences between comets native to our solar system and interstellar interlopers. Lemmon originated approximately 4.66 billion years ago within the disk of gas and dust surrounding the nascent sun, likely in the region beyond Neptune, where temperatures were sufficiently frigid for water and other volatiles to condense as ice. Gravitational perturbations from the giant planets eventually scattered it into the Oort cloud, that immense spherical reservoir of comets encircling the solar system at distances extending up to 100,000 astronomical units. Subsequently, some event, perhaps the gravitational influence of a passing star or a vast molecular cloud, perturbed Lemmon's orbit, initiating its descent back toward the Sun on the journey we are currently observing. Its composition reflects the primordial chemistry of our solar system, specifically the isotopic ratios and molecular abundances present in our galactic neighborhood 4 billion years ago. 3 Atlas, on the other hand, formed elsewhere, around a different star, under conditions that may have been similar or radically divergent. Factors such as the temperature and pressure within that protostellar disk, the abundance of heavy elements, the radiation environment, and the timing of planetary formation all influence a comet's composition and structure. By comparing interstellar comets with those originating within our solar system, we are essentially examining samples from different stellar nurseries, seeking commonalities that reveal universal processes and disparities that underscore local variations. Lemmon serves as a tangible, real-time illustration of cometary fragility. Every comet faces a gamble against disintegration. The majority survive their perihelion passage, shedding some mass through sublimation, retreating to the outer solar system or beyond, remaining intact. Some fragment spectacularly, offering dramatic visual displays as multiple nuclei and expanding dust clouds surge in brightness before fading. A few vanish entirely, obliterated to such an extent that subsequent tracking becomes impossible. Observing Lemmon during its peak visibility window transcends mere appreciation of a celestial marvel. It involves witnessing a survivor, an entity that has endured billions of years in the profound cold of the Oort cloud and is now navigating a gauntlet of solar heat and radiation that may ultimately lead to its demise. The timing is opportune. While 3 Atlas is obscured behind the sun, Lemmon provides a readily accessible alternative, a distinct comet available for study. If you have never personally witnessed a comet, having only encountered them through screen images or textbook diagrams, this is your opportunity. Venture outdoors before dawn. Find a location with minimal light pollution. Allow your eyes about 10 to 15 minutes to adjust, and scan the eastern sky within the constellation Cancer. That faint, hazy patch of light, should you find it, contains ice that predates Earth's formation, organic molecules that existed before life arose, and silicate dust older than our planet. You are observing a messenger from the dawn of the solar system, and within 2 weeks it will recede from view. Its brief moment of prominence is fleeting. Its ultimate destiny, whether survival or disintegration, remains unwritten. Observe the heavens now, while Atlas is hidden. Part 7. The Swan and the Context. Comets often appear to arrive in clusters, or at least this is the perception of those tracking these icy visitors. In reality, the situation is more mundane. At any given moment, numerous comets orbit the Sun at varying distances, most too faint to be observed without powerful telescopes. A select few possess sufficient brightness to capture the attention of amateur astronomers, and very rarely one emerges with such spectacular brilliance that it becomes visible to the naked eye and captures the public imagination. The perceived groupings are largely a consequence of observational biases and the statistical nature of comet discoveries, yet they do create periods where comet watchers have multiple targets to consider. The year 2025 is shaping up to be one such period. Alongside Lemmon and the elusive Three-Eye Atlas, another comet, designated C2025 R2 Swan, has entered the astronomical catalogue. The Swan designation refers to the solar wind anisotropies instrument aboard the SOHO spacecraft, which observes the sky in ultraviolet wavelengths sensitive to hydrogen emission. Comets generate vast hydrogen clouds, formed from neutral hydrogen atoms created when water molecules break apart under solar ultraviolet radiation. These clouds are invisible to optical telescopes, but glow intensely at specific UV wavelengths, allowing the SWAN instrument to detect them from great distances, sometimes spotting comets months before they become observable from Earth-based observatories. C2025 R2 Swan was initially identified through its hydrogen corona, that immense, invisible envelope surrounding its visible coma. Subsequent optical observations confirmed the discovery and enabled trajectory calculations. The comet is following a highly elongated elliptical orbit that will bring it to perihelion in early 2026, well after Lemmon's close approach, but soon enough to sustain interest among comet observers as they prepare their equipment and observation strategies. Initial brightness estimates for Swan suggest it may reach a magnitude of 6 or 7 at perihelion, rendering it a binocular object, but likely not visible to the naked eye except under exceptional circumstances. The predicted brightness is contingent upon assumptions regarding nucleus size and activity level, both of which remain uncertain. Some comets discovered by Swan have surpassed expectations, significantly brightening as they approach the Sun. Others have been disappointing, remaining faint and diffuse despite optimistic predictions. The only definitive way to ascertain their behavior is through continued observation. One intriguing possibility associated with newly discovered comets involves meteor showers. As a comet nears the Sun, it sheds dust particles that disperse along its orbital path, forming a trail of debris. When Earth's orbit intersects this dust stream, the particles impact our atmosphere at high velocities, typically 30 to 70 kilometers per second, vaporizing and creating bright streaks we perceive as meteors or shooting stars. Most annual meteor showers, such as the Perseids in August or the Geminids in December, result from Earth passing through well-established dust trails left by comets that have made numerous perihelion passages, depositing dust over centuries or millennia. New comets making their initial transit through the inner solar system can generate unpredictable meteor activity. The distribution of dust along their orbits has not yet been smoothed out by repeated passages and gravitational influences. Fresh outbursts may create dense clumps of particles, and if Earth happens to traverse one of these concentrations, meteor rates could spike dramatically, leading to a meteor storm with hundreds or even thousands of visible meteors per hour. Such events are rare and difficult to predict because they depend on the precise spatial distribution of dust, a factor we cannot directly measure. Swan's orbit will be meticulously calculated in the coming months, allowing astronomers to determine if any potential intersections with Earth's orbital path might occur. Even a low probability of a meteor shower ignites excitement among comet and meteor enthusiasts. Witnessing a meteor storm is a once-in-a-lifetime experience, a celestial fireworks display that occurs perhaps once or twice per generation. The meteors appear to radiate from a specific point in the sky known as the radiant, where parallel particle trajectories entering the atmosphere converge due to perspective. During a storm, the entire sky seems to rain meteors, with streaks of light appearing in all directions, overwhelming the senses in a manner that photographs can never fully convey. However, for every comet that brightens and performs as anticipated, several others fizzle. The history of comet astronomy is replete with failed predictions, with objects expected to become magnificent comets instead remaining faint and unremarkable. Comet Kohoutek in 1973 was predicted to become one of the brightest comets of the century, but barely achieved naked-eye visibility, disappointing millions who had been promised a spectacular celestial event. Comet Ison in 2013 was expected to survive perihelion and brighten dramatically, but instead disintegrated. These disappointments instill humility and underscore how much we still have to learn about cometary physics. The comparative analysis of Swan's and Lemmon's brightness curves will ultimately yield valuable scientific data. Observing two comets simultaneously under similar solar conditions allows for a direct comparison of their activity levels and sublimation physics. Differences in brightness at comparable distances from the Sun would indicate variations in nucleus size, composition, or surface properties. If one comet is predominantly water-driven and the other carbon monoxide-driven, their activity profiles will diverge in characteristic ways. If one fragments and the other does not, we gain insights into structural differences that influence susceptibility to fragmentation. The contrasting behaviors of Swan and Lemmon create a compelling narrative. Many comets falter. Will 3 Atlas also fail? Is there something about the current solar environment that diminishes the likelihood of cometary survival? The October 2025 coronal hole event could have been an isolated anomaly, or it might signal a period of heightened solar activity that poses a threat to any comet traversing the inner solar system. The Sun's 11-year activity cycle is approaching its solar maximum, the phase characterized by frequent sunspots and coronal mass ejections, and increased solar wind speeds and magnetic field strengths. Comets approaching perihelion during solar maximum encounter more challenging conditions than those that arrive during solar minimum. Historical comet fragmentation data offers sobering statistics. The tidal disruption of comet Shoemaker-Levy 9 by Jupiter in 1992, followed by its spectacular impacts in 1994, demonstrated the thoroughness with which a comet can be destroyed by gravitational and tidal forces. Comet 73P Schwarzmann-Wachmann, 3 fragmented during its 1995 appearance, splitting into multiple pieces that progressively separated over subsequent years. By its 2011 return, The comet had fractured into more than 60 identified fragments, forming a debris field spread across several thousand kilometers of its orbit. Some fragments remained active, exhibiting small comas, while others appeared dormant, their volatile materials depleted or sealed beneath inactive crusts. These fragmentation events have significant implications for predicting space hazards. A single, large comet nucleus poses a minimal risk to Earth because the probability of a nucleus measuring only a few kilometers across impacting our planet is exceedingly small. However, a fragmenting comet generates dozens or hundreds of pieces, each capable of atmospheric entry. While these individual fragments are smaller and less destructive than the original nucleus, the likelihood of one of them intersecting Earth's path increases. Most comet fragments burn up harmlessly in the atmosphere or miss Earth entirely, but the risk calculation shifts when dealing with dispersed debris rather than a singular object. The impending arrival of Comet C 2024 S1, ISON, predicted to be the brightest comet apparition of the century, places current observations in perspective. Comets act as the solar system's chaotic chronometers, appearing unpredictably, brightening erratically, and fragmenting without warning. They mark time in human consciousness differently than the regular celestial motions of planets and stars. A generation remembers Halley's Comet in 1986, which offered a disappointing view for most, but held cultural significance. The preceding generation remembers Comet Hale-Bopp in 1997, visible to the naked eye for months, and bright enough to be seen even from urban centres. The current generation may remember Lemmon, Swan, or Three-Eye Atlas, assuming they survive and brighten sufficiently. Are we experiencing a period of unusual cometary appearances? Statistical analyses of comet discovery rates over decades reveal fluctuations that may indicate genuine clustering or simply reflect advancements in detection technology. An increasing number of telescopes scanning larger areas of the sky with greater sensitivity naturally leads to the discovery of more comets. The Atlas survey, which discovered Comet Three-Eye Atlas, is specifically designed to locate near-Earth objects and incidentally finds comets. Surveys like the Catalina Sky Survey, Mount Lemmon Observatory, and Pan-STARRS in Hawaii utilize automated systems that constantly monitor the sky for any moving objects, including comets. However, there is a tantalizing hint in the data that the Oort cloud, that distant reservoir of comets, might be subjected to perturbations that send showers of comets towards the inner solar system. Such disturbances could be caused by passing stars, gravitational interactions with giant molecular clouds in the galaxy, or even the solar system's vertical oscillation through the galactic plane as it orbits the Milky Way's center. Any of these events could dislodge comets from their distant perches. Should these celestial events be genuine, they would unfold over spans of millions of years, far exceeding the temporal horizon for direct human observation. Nevertheless, the geological strata may hold clues, with evidence of impact clustering potentially illuminating these ancient bombardments that assailed the inner solar system during the epoch of the dinosaurs, or even further back in Earth's primordial history. Comets serve as the solar system's unpredictable chronometers precisely because their trajectories diverge from the regular, calculable paths of planets. Most planets maintain nearly circular orbits, their future positions predictable with remarkable accuracy centuries ahead. Comets, however, originate from the distant darkness, embarking on highly eccentric journeys. Their cyclical appearances, if they recur at all, can span decades, centuries, or millennia. Some are novel visitors, making their maiden voyages from the Oort cloud. Others are short-period comets, ensnared by Jupiter's gravitational pull into orbits that necessitate their return every few years. These celestial wanderers remind us that our solar system is not a precisely wound clockwork mechanism of perfect orbits, but rather a dynamic, volatile domain where gravitational interactions incessantly reshape trajectories and new cosmic entities emerge without prior notice. Part 8. The Unwavering Signal. While celestial observers meticulously scan the heavens for comets and monitor the solar wind, a distinct cosmic endeavor is simultaneously unfolding within laboratories and terrestrial ground stations. In the year 2025, China declared the successful completion of the world's most extensive quantum communication network, a colossal system spanning 12,900 kilometers that links Beijing with remote ground installations via satellite relays. This achievement was accompanied by the assertion that the network provides data transmission that is virtually impervious to interception. The announcement signifies a pivotal moment in the unfolding quantum information revolution. Furthermore, if the system performs as proclaimed, it stands to fundamentally alter the panorama of global communications and cybersecurity, with implications extending far beyond immediate military or commercial interests. Quantum key distribution, the foundational technology underpinning this advancement, leverages the fundamental principles of quantum mechanics to detect any unauthorized attempts at eavesdropping. The core concept is as elegant as it is profoundly peculiar. Information is encoded within the quantum states of photons, which are individual particles of light. These photons are then transmitted through optical fibers or across the expanse of space between satellites and ground stations. The quantum no-cloning theorem guarantees that these delicate quantum states cannot be replicated with perfect fidelity. Any attempt to measure or intercept these photons invariably perturbs them in ways that are readily detectable. This inherent property ensures that two parties engaged in a quantum communication exchange can generate encryption keys and possess absolute certainty regarding any illicit efforts to intercept those keys during transmission. The process commences with the generation of entangled photons, pairs of particles that are created concurrently and share an intrinsic quantum linkage. This connection is such that measuring a property of one photon instantaneously influences the other, irrespective of the spatial distance separating them. This phenomenon, famously dubbed spooky action at a distance by Einstein, has been repeatedly confirmed through numerous experiments and forms the bedrock for several nascent quantum technologies, including quantum computing and quantum teleportation. In the context of quantum key distribution, entangled photons enable two parties to establish a shared pool of random numbers, which can then be utilized as cryptographic keys. The practical implementation of this technology demands extraordinary precision. Photons must be generated, entangled, transmitted, and detected with minimal loss and maximal accuracy. Optical systems must precisely align satellite-mounted transceivers with ground stations situated hundreds or even thousands of kilometers apart, while simultaneously compensating for atmospheric disturbances, the motion of the satellites, and the Earth's rotation. Single-photon detectors are tasked with registering individual particles arriving at rates ranging from thousands to millions per second, meticulously distinguishing genuine signals from ambient background noise and spurious detector activations. Error correction protocols are essential to account for inherent imperfections, while still upholding the paramount objective of security. China's advanced system relies on the Messius satellite, launched in 2016 and named in honor of an ancient Chinese philosopher. This satellite maintains an orbital altitude of approximately 500 kilometers, traversing predetermined paths over ground stations in a sun-synchronous orbit that ensures regular communication windows. During each orbital pass, which lasts for several minutes, the satellite disseminates entangled photons to synchronized pairs of ground stations, thereby facilitating the establishment of shared encryption keys. These keys subsequently secure conventional data transmissions employing standard encryption algorithms, with the quantum channel serving as the ultimate guarantor that the keys themselves have remained uncompromised. The recent expansion to a 12,900-kilometer network represents a substantial engineering feat. Earlier demonstrations were confined to shorter distances or necessitated the use of trusted relay stations, which, in theory, could have been compromised. The novel system chains together quantum links across multiple satellite passes and ground stations, thereby establishing end-to-end security on a continental scale. According to Chinese researchers, this network is already operational, serving government and financial institutions and safeguarding communications against both existing and prospective decryption threats. This last point is of critical importance. Contemporary encryption systems, those currently safeguarding everything from financial transactions to sensitive government communications, are predicated on complex mathematical problems that pose significant computational challenges for classical computers. Examples include the factorization of large numbers or the computation of discrete logarithms. These tasks demand such extensive computational time that breaking encryption becomes practically unfeasible, even with the most powerful supercomputers available. However, quantum computers, should they be developed to a sufficient scale, possess the capability to resolve these problems with unprecedented efficiency, thereby rendering current encryption methods obsolete. Data encrypted today and intercepted by adversaries could be decrypted years or even decades in the future, once quantum computers reach maturity. Quantum key distribution offers a robust defense against this harvest now, decrypt later threat, because its security is not contingent on computational difficulty, but on the fundamental laws of physics. Western nations, notably the United States and various European countries, observe China's advancements in quantum communications with considerable apprehension. The MIT Technology Review's Quantum Index, published in 2025, positions China as a leader in several key quantum technology metrics, including quantum communications and quantum sensing. American research initiatives are actively striving to bridge this gap, with the Department of Energy providing funding for quantum network testbeds and DARPA exploring space-based quantum communication architectures. Nevertheless, China's early lead and substantial governmental investment have created a discernible quantum disparity, a development that causes considerable concern among defense planners and technology strategists. The policy ramifications extend beyond mere technological competition. If quantum communication networks evolve into the foundational infrastructure for future secure communications, nations lacking access to this technology face the prospect of a significant informational disadvantage. International agreements governing the development of quantum technologies remain nascent. Crucial questions regarding export controls, technology transfer, and standardization remain unresolved. Some researchers advocate for open collaboration and the shared development of quantum networks as global infrastructure, drawing parallels to the way the Internet evolved as an international resource. Others champion a strategy of competitive advantage and restricted access, viewing quantum superiority as an indispensable strategic asset too valuable to be shared. Could space-based quantum networks indeed become the backbone of the future Internet? This vision entails constellations of quantum satellites providing comprehensive global coverage, ground stations situated in every major urban center, and quantum repeaters extending the range of communication beyond direct line-of-sight limitations. Data would traverse these networks encrypted by quantum keys that are continuously refreshed, rendering them immune to interception and even resilient against future technologies that are currently beyond our imagination. The system would seamlessly integrate with existing fiber optic networks, establishing a hybrid classical quantum infrastructure where quantum channels are responsible for key distribution, while classical channels handle the transmission of bulk data. Conspiracies and speculations naturally emerge around technologies that are as advanced and as shrouded in secrecy as these quantum systems. Quantum key distribution mechanisms necessitate extensive testing and calibration procedures that generate a wealth of data concerning photon transmission statistics, detector efficacy, and error rates. A significant portion of this data is classified or held as proprietary information. Chinese scholarly publications offer descriptions of the system's capabilities in general terms, but conspicuously omit the granular engineering details that would permit independent verification or replication. Western intelligence agencies are undoubtedly engaged in close monitoring of the program through signals intelligence and other methodologies, aiming to ascertain its actual capabilities relative to its publicly stated claims. This inherent opacity fuels speculation regarding whether the system functions as advertised or if undisclosed vulnerabilities exist. Some express concerns about the potential for pervasive state surveillance. A government in control of a nationwide quantum communication network would possess an unprecedented capacity to monitor the communication patterns between individuals, even if the content of those communications remains encrypted. Metadata, the information detailing communication flows rather than their substance, often reveals as much as the messages themselves. Traffic analysis techniques can be employed to identify social networks, track movements, and predict behavior. A quantum network that meticulously logs every connection, every photon transmission, and every key generation event effectively constructs a surveillance infrastructure of staggering scope. The connection to the narrative of the three-eyed atlas is rooted in a fascinating parallel. Just as comets carry intrinsic information from distant star systems, encoded not in linguistic form, but in their chemical composition and isotopic ratios, humanity is now constructing systems to convey unbreakable, encoded messages across our own planet. Both represent forms of information that possess the resilience to endure hostile environments. Comet chemistry survives the harshness of interstellar space and the intense heat of the sun, while quantum keys withstand the machinations of active adversaries intent on interception. Both endeavors push the boundaries of what is presently achievable. Comets, as natural information carriers, are shaped by billions of years of physical processes. Quantum networks, in contrast, are artificial information carriers forged through decades of engineering innovation. Numerous unknowns persist. Current quantum key distribution rates, typically measured in kilobits per second, significantly lag behind classical communication speeds, which are measured in gigabits or even terabits per second. Scaling quantum networks to accommodate internet-level traffic necessitates either dramatic improvements in photon transmission and detection efficiency, or the development of fundamentally novel approaches to quantum networking. Decoherence, the gradual degradation of quantum properties due to interactions with the surrounding environment, imposes fundamental limitations on the duration for which quantum states can be maintained and the distances over which they can be reliably transmitted. Satellites play a crucial role in extending communication range by operating within the vacuum of space, above the majority of the Earth's atmosphere. However, atmospheric turbulence encountered at ground stations continues to degrade performance. Endpoint security presents an additional significant challenge. Quantum key distribution guarantees the secure transmission of encryption keys, but these keys must ultimately be employed by classical computers to encrypt and decrypt data. If these classical computers are compromised, whether through malware, physical intrusion, or side-channel attacks that exploit electromagnetic emissions or power consumption, the previously unbreakable quantum keys become rendered entirely irrelevant. Security, in essence, is only as robust as its weakest link, and in any practical system, weak links are invariably abundant. The narrative of the quantum space race accurately captures a fundamental aspect of human nature and technological advancement: competition. We engage in rivalry, even in our pursuit of understanding and harnessing the fundamental laws of physics. Quantum mechanics, arguably the most successful physical theory ever developed in terms of its predictive accuracy and technological impact, has now become a focal point of geopolitical competition. The very quantum principles that elucidate atomic structure and chemical bonding are now being instrumentalized to secure communications and promise revolutionary computational capabilities. Nations are investing billions in quantum research, not solely out of an insatiable scientific curiosity, but because quantum technology has the potential to profoundly influence the military balance and economic leadership in the decades to come. Whether this intense competition spurs innovation at a faster pace than collaborative efforts would, and whether the benefits derived from quantum networks will be shared globally or concentrated within a select group of technologically advanced nations, remain open questions as this critical race accelerates. Part 9. The internal circular economy. Science occasionally yields discoveries so unexpected, so contrary to conventional intuition, that they compel us to re-evaluate our fundamental assumptions about what is conceivable. The recent announcement that synthetic biologists have successfully engineered yeast capable of converting human urine into hydroxyapatite, a mineral component of bone, represents one such paradigm-shifting breakthrough. The potential applications span medical and ecological domains, and the broader implications delve into the intrinsic value of waste and the remarkable capacity of biological systems to be reprogrammed for transformative material conversions. Urea, the primary nitrogen-containing constituent of urine, functions as a waste product in mammalian metabolism. As proteins degrade within the body, amino acids undergo metabolic processing, and the nitrogen they contain must be excreted. Aquatic organisms excrete ammonia directly, a straightforward and energetically economical solution when one resides in an aqueous environment that facilitates the dilution and dispersal of this toxic compound. Terrestrial animals, however, face a different challenge. While ammonia is toxic and accumulates readily, the conservation of water is paramount. Consequently, terrestrial animals have evolved more sophisticated strategies. Birds and reptiles produce uric acid, a relatively insoluble compound that precipitates out and can be excreted as a paste, thereby minimizing water loss. Mammals, on the other hand, produce urea, a compound sufficiently soluble for transport in water, yet less toxic than ammonia, and excreted in liquid urine as a compromise between water conservation and waste elimination. Humans generate approximately 1 to 2 liters of urine daily, a volume influenced by fluid intake and metabolic rate, containing roughly 20 to 30 grams of urea. This equates to approximately 10 kilograms of urea per person annually. When extrapolated across the global population of 8 billion individuals, This amounts to an astonishing 80 million metric tons of urea excreted each year. Currently, this urea typically enters sewage systems, where it is either biodegraded by bacteria or released directly into the environment. The novel approach employing synthetic biology poses a fundamental question. Could this waste stream be ingeniously transformed into something of significant value? Hydroxyapatite is the mineral constituent of bones and teeth, a calcium phosphate compound with the chemical formula C10PO4-6OH2. It provides the requisite hardness and structural integrity that enables bones to bear body weight and shield vital organs. Natural bone is a composite material characterized by hydroxyapatite crystals embedded within a collagen protein matrix, thus harmonizing the hardness of the mineral component with the inherent flexibility and resilience of organic fibers. Medical applications necessitate the use of pure hydroxyapatite for bone grafts, dental implants, and reconstructive surgical procedures. At present, hydroxyapatite is synthesized through chemical processes or harvested from animal bones. Both of these methods present limitations concerning purity, crystalline structure, and production cost. The engineered yeast methodology operates through metabolic pathway engineering. Researchers have meticulously identified the sequence of enzymatic reactions essential for converting urea into the chemical precursors of hydroxyapatite. Subsequently, genes encoding these specific enzymes were introduced into yeast cells. The yeast, commonly known as Saccharomyces cerevisiae, and widely utilized in brewing and baking, now harbors synthetic metabolic pathways that are not naturally present. When these modified yeast cells are supplied with urine as a nitrogen source and provided with calcium and phosphate ions, they commence the production of hydroxyapatite crystals, which then precipitate out and can be harvested. The intricate mechanism involves a series of steps. The enzyme urease acts upon urea, breaking it down into ammonia and carbon dioxide. The liberated ammonia is then integrated into amino acid synthesis pathways, while the carbon dioxide, along with additional calcium and phosphate ions, undergoes mineralization reactions that ultimately yield hydroxyapatite. The precise crystallographic characteristics of the resulting product, including the size, shape, and purity of the hydroxyapatite crystals, are contingent upon the specific reaction conditions such as pH, temperature, ion concentrations, and the genetic programming of the yeast's metabolic pathways. Initial findings are promising, demonstrating the production of hydroxyapatite with properties akin to natural bone mineral. However, substantial optimization efforts are still required before the process can be considered practical for widespread medical applications. The current efficiency and yield rates presently limit immediate practical deployment. The yeast produces hydroxyapatite at concentrations too low for commercial viability, necessitating the use of exceedingly large bioreactor volumes to generate quantities of meaningful scale. Challenges related to purification also emerge, as the hydroxyapatite must be effectively separated from the yeast cells, components of the growth medium, and various metabolic byproducts. Purity is a critically important factor for medical applications. The presence of extraneous proteins or bacterial endotoxins within implanted hydroxyapatite could potentially trigger adverse immune responses or initiate infections. Achieving medical-grade purity from a biological production system demands rigorous quality control measures and sophisticated purification protocols. Nevertheless, the underlying potential is truly transformative. Bone fractures affect millions of individuals annually. While the majority of these fractures heal naturally, complex breaks or bone loss resulting from disease or trauma frequently necessitate the use of grafts or synthetic materials to facilitate healing. Current bone graft materials encompass autografts, harvested from the patient's own body, allografts, sourced from cadavers, and synthetic ceramics. Each of these options carries its own set of drawbacks. Autograft procedures require an additional surgical intervention to harvest the graft tissue. Allografts, while effective, carry a minimal risk of disease transmission and potential immune rejection. Synthetic ceramics sometimes exhibit suboptimal integration with natural bone tissue. Hydroxyapatite produced biologically from waste materials could potentially offer an abundant and cost-effective alternative, provided that the challenges associated with its production and purification are successfully addressed. Dental implants represent another significant market. Hydroxyapatite coatings applied to titanium implants demonstrably enhance osseointegration, the crucial process of bonding between the implant and the jawbone. Current coating techniques involve the use of hydroxyapatite produced through high-temperature chemical sintering, an energy-intensive manufacturing process. Biological production at ambient temperatures in an aqueous solution would considerably reduce energy consumption and the associated carbon footprint, while also potentially yielding crystal structures that more closely resemble natural bone and thus integrate more effectively with living tissues. The ecological benefits extend beyond the direct application of the manufactured material. Urea present in wastewater contributes significantly to eutrophication when it is released into rivers and coastal waters. Excessive nitrogen levels stimulate algal growth, leading to harmful blooms that deplete dissolved oxygen levels and create dead zones devoid of marine life. By capturing urea and converting it into a solid mineral form, nitrogen is effectively removed from the waste stream, thereby mitigating its detrimental environmental impact. This process exemplifies waste valorization, the principle of treating waste materials not as a disposal problem, but as a valuable resource. Controversies are naturally likely to arise concerning the utilization of human waste products in the creation of medical materials. Cultural taboos surrounding urine and feces are deeply ingrained. Even though, from an intellectual standpoint, we understand that purified compounds possess no residual memory of their origin. The calcium atoms within hydroxyapatite derived from urine are chemically identical to those from any other source, and that the material, once purified, carries no trace of its waste origin beyond the historical fact of its production pathway. Psychological resistance persists. Would patients readily accept bone grafts or dental implants produced from urine? Would regulatory agencies grant approval for such materials for human use? These questions delve more into cultural values and perceptions of risk than into technical feasibility. Applications for astronauts may present the most compelling use case. Inhabitants of Mars colonies or individuals undertaking long-duration space missions will face severe resource constraints, rendering every opportunity for recycling immensely valuable. Crew members will consistently produce urine daily, and this urine contains essential nitrogen and other elements that must be processed and either recycled or disposed of. Converting urine into usable hydroxyapatite for medical purposes or for the fabrication of structural materials would represent a highly efficient solution, addressing waste management while simultaneously producing indispensable materials. The closed-loop life support systems essential for space exploration necessitate a design philosophy centered on maximizing recycling and minimizing waste. What you discard could literally preserve your life if a bone defect on Mars necessitates a repair, and the sole source of hydroxyapatite available originates from recycled crew urine. Resistance from major corporations to embracing circular biotechnologies stems from anticipated disruption rather than proven malfeasance. The pharmaceutical and medical device sectors currently thrive on existing production methodologies and established supply networks. Innovations that challenge prevalent business models inevitably encounter opposition, irrespective of their technical sophistication. Whether this opposition materializes for urine-derived hydroxyapatite will hinge on factors such as manufacturing expense, scalability, regulatory approvals, and the intellectual property landscape. Should the technology be patentable and controllable by established entities, its integration becomes more probable. Conversely, if it threatens to devalue a high-profit product, opposition is more likely. The broader lesson extends beyond any singular application. Nature operates on principles of absolute efficiency. Nothing is wasted. Nutrients continuously circulate throughout ecological systems. The byproducts of one organism serve as sustenance for another. Energy flows, and elements are perpetually recycled. Humanity's ancestral cultures managed waste with relative ease due to low population densities and the pervasive natural processes that efficiently decomposed and repurposed most waste. Industrialization and rapid urbanization fundamentally altered these natural cycles, generating waste streams that now far exceed nature's capacity for recycling. Synthetic biology presents the tools to artificially re-establish these vital cycles. This involves engineering organisms to fulfill ecological roles that do not naturally exist, but are essential for human needs. Transforming urine into bone mineral is merely one illustration of this principle. The same fundamental concept applies to converting atmospheric carbon dioxide into usable fuel, repurposing plastic debris into biodegradable polymers, and extracting valuable chemicals from agricultural runoff. We are now learning to reinstate the closed-loop systems that our technological advancements initially disrupted, effectively catching up to the circular economy that nature has perfected over eons. Part 10. The Universal Yawn. The study of animal behavior offers a rich tapestry of fascination, primarily because it reflects cognitive and emotional states familiar to us, yet expressed by creatures whose inner lives remain largely enigmatic. The phenomenon of contagious yawning, where observing another yawn instigates an undeniable urge to do the same, was until recently believed to be exclusive to humans and a select group of highly social mammals such as chimpanzees and canines. However, the recent publication of research demonstrating contagious yawning in zebrafish challenges this long-held assumption, posing intriguing questions about the evolutionary origins and underlying neural mechanisms of this behavior. Zebrafish, small freshwater fish indigenous to the rivers of South Asia and widely kept in research laboratories and home aquariums, have become invaluable model organisms for understanding vertebrate development and behavior. Their transparent embryos allow researchers to visualize organogenesis in real time under microscopy. Their genetic makeup is thoroughly understood, with established methods for gene manipulation and observation of the resulting effects. Furthermore, their small size, affordability of maintenance, and prolific offspring production make them ideal for extensive experimental studies. Nevertheless, contagious yawning was an entirely unexpected discovery in this species. The experimental setup involved positioning zebrafish in adjacent tanks where they could visually interact through transparent partitions. Researchers induced yawning in one fish through a controlled reduction in oxygen levels, a known stimulus for yawning across numerous species. High-speed cameras meticulously documented the behavior of both the yawning fish and the observing individuals. Subsequent analysis revealed a statistically significant increase in yawning frequency among the observer fish following the observation of a neighboring fish yawning, with temporal correlations strongly suggesting genuine contagion rather than coincidental yawning triggered by shared environmental stimuli. The remarkable nature of this finding lies in the prevailing belief that contagious yawning requires the presence of mirror neurons or analogous neural circuitry capable of mentally simulating the actions and states of others. These neural pathways, predominantly found in primate brains and suspected in certain social mammals, are considered the foundation for empathy, observational learning, and the ability to infer mental states. Fish brains, however, lack the cortical structures that house mammalian mirror neurons. Their neural organization is fundamentally different, possessing a simpler architecture in certain aspects, although it is by no means rudimentary overall. The presence of contagious yawning in zebrafish implies either that the behavior does not necessitate the complex neural machinery previously theorized, or that convergent evolution has produced analogous circuitry in fish through entirely distinct anatomical routes. The precise neural circuits governing yawning in any species remain incompletely elucidated. The act itself involves the synchronized contraction of muscles in the jaw, facial region, throat, and respiratory system, culminating in the characteristic wide opening of the mouth, a deep inhalation, followed by a slower exhalation. Once initiated, the behavior appears to be involuntary, resisting conscious suppression even in social contexts where yawning might be deemed inappropriate. A diverse array of triggers exists, including fatigue, boredom, diminished oxygen levels, and the visual cue of another individual yawning. The variety of triggers suggests the convergence of multiple neural pathways onto a common motor output. In humans, contagious yawning increases during childhood development, peaks in early adulthood, and exhibits a correlation with empathy levels. Individuals who score highly on empathy questionnaires are more prone to yawn when observing others yawn. Conversely, individuals diagnosed with autism spectrum disorders, who often face challenges in social cognition and empathy, demonstrate reduced contagious yawning. These observed correlations lend support to the hypothesis that contagious yawning is reliant on neural systems involved in social cognition and emotional resonance. The discovery of this same behavior in zebrafish, creatures not typically associated with empathy or sophisticated social cognition, complicates this seemingly straightforward narrative. The evolutionary puzzle deepens when considering the taxonomic distribution of this behavior. Contagious yawning has been observed in humans, chimpanzees, bonobos, dogs, and now zebrafish. It appears to be absent or has not yet been demonstrated in many tested species, including cats, horses, and most avian species. This scattered pattern across the animal kingdom suggests either multiple independent evolutionary origins of the behavior or an ancient origin followed by its subsequent loss in numerous lineages. Neither explanation provides a fully satisfactory resolution. The concept of convergent evolution for a behavior as specific as contagious yawning appearing independently in mammals and fish seems improbable unless the behavior serves a crucial yet unrecognized function. An ancient origin necessitates explaining why such a wide array of species would subsequently lose this trait. Hypotheses regarding its function are varied. One proposal posits that contagious yawning serves to enhance group coordination, synchronizing states of arousal or attention within social groups. If a single individual detects an environmental change that triggers yawning, perhaps signaling a transition from alertness to rest, the propagation of this signal throughout the group could facilitate coordinated collective behavior. Fish schools undoubtedly rely on coordination. They move in unison, executing synchronized turns, maintaining precise inter-individual spacing, and responding to threats with unified evasive maneuvers. Could contagious yawning be an integral component of the behavioral repertoire that enables this level of coordination? Another hypothesis focuses on stress reduction and social bonding. Yawning may function to regulate stress hormones or reset neural states during periods of social stress. The act of observing others yawn and subsequently yawning in response could create a feedback loop that aids groups in collectively managing tension. Zebrafish are inherently social animals that school in their natural habitats, and their social dynamics involve dominance hierarchies, competition for mates, and vigilance against predators. It is plausible that contagious yawning plays a role in maintaining group cohesion under stressful conditions. The crux of the debate lies in whether the behavior observed in zebrafish genuinely constitutes yawning, or is instead a different type of jaw movement or gill action being misclassified. Fish do not breathe atmospheric air under typical circumstances, meaning the respiratory component of mammalian yawning lacks a direct equivalent. The gaping mouth motion observed in zebrafish could serve alternative physiological functions related to gill ventilation or feeding. Critics contend that without clear evidence that the fish behavior shares the same neural triggers and physiological outcomes as mammalian yawning, labeling it as contagious yawning amounts to anthropomorphizing a superficially similar, yet functionally distinct behavior. Proponents argue, however, that the behavior shares key characteristics with mammalian yawning, including its involuntary nature, a stereotyped motor pattern, and triggers such as hypoxia and the demonstrated social contagion. While the neural pathways may differ between fish and mammals, separated by hundreds of millions of years of evolutionary divergence, if the behavior serves analogous functions and responds to similar stimuli, then the term yawning remains applicable. Biology is replete with examples of convergent evolution where disparate structures perform similar functions. The wings of birds and bats, for instance, are anatomically distinct yet functionally equivalent. It is conceivable that yawning in fish and mammals represents convergent solutions to comparable behavioral or physiological challenges. Speculation extends into more profound biological territory. Could yawn contagion represent a universal signaling mechanism, an ancient communication channel that predates more complex social cognition? It is possible that the fundamental neural circuitry underlying contagious yawning evolved early in vertebrate history, preserved across hundreds of millions of years, because it serves essential coordination functions in social species. This would imply that the behavior provides substantial fitness advantages, enhancing survival or reproduction, to a degree that natural selection actively maintains it, despite the neural machinery required. A more speculative possibility, rarely articulated in academic circles but sometimes discussed informally, is whether synchronization phenomena extend beyond individual species, potentially even across entire kingdoms of life. Yawn contagion, as currently understood, operates through sensory perception. Observing or hearing someone yawn triggers neural pathways that subsequently induce yawning. However, broader synchronization in nature occurs through mechanisms that are only beginning to be understood. Heart cells in culture synchronize their rhythmic beating through electrical and chemical signaling. Fireflies in the Southeast Asian mangroves synchronize their flashing across hundreds of individuals. Could there be fundamental biological principles of synchrony and resonance that manifest in yawn contagion alongside other phenomena? The narrative connection to cosmic themes is established through the concept of resonance and synchronization across scales. Fish schools move as cohesive units, responding to each other's movements via lateral line sensors that detect changes in water pressure. Flocks of birds execute simultaneous turns, with each individual adhering to simple rules regarding spacing and alignment, leading to the emergence of complex collective patterns. At larger scales, planets orbit in resonant configurations, their gravitational interactions locking their orbital periods into precise integer ratios. Jupiter's moons Io, Europa, and Ganymede orbit in a 4.2.1 resonance, with each orbital configuration repeating predictably. On cosmic scales, galaxy clusters interact gravitationally, the dynamics coupled across millions of light-years. Synchronization emerges as a fundamental principle governing the organization of systems from the molecular to the cosmic level. Oscillators, whether they are neurons firing, hearts beating, pendulums swinging, or planets orbiting, tend to achieve phase lock when coupled, their rhythms and frequencies aligning to common values. The mathematical framework describing coupled oscillators reveals surprising commonalities across vastly different physical systems. It is plausible that yawn contagion represents a biological manifestation of these universal principles of synchronization, a social oscillator that couples through observation and triggers synchronized responses. Human brains and stars might share more commonalities than initially perceived if we shift our perspective from specific mechanisms to abstract principles. Both are intricate dynamical systems possessing internal structure, emergent properties, and couplings to their external environments. Both process information, albeit through radically different means and at vastly disparate scales. Brains process sensory inputs and generate behavioral outputs via electrochemical signaling across neural networks. Stars process gravitational inputs and generate radiation outputs through nuclear fusion, regulated by hydrostatic and thermal equilibrium. While the analogy quickly breaks down if pushed too far, it points towards profound questions concerning complexity, information, and organization within the universe. The zebrafish study, at its core, serves as a potent reminder of how much we still have to learn about the minds and behaviors of animals. Every assumption, every ostensibly established fact regarding animal capabilities remains provisional and subject to revision upon the emergence of new evidence. We once believed contagious yawning to be dependent on empathy and mirror neurons. Apparently, fish did not receive this memo. What other behaviors we currently deem exclusively human or mammalian might possess deeper evolutionary roots or a broader distribution than we currently recognize? Tool use is observed in birds and octopuses. Culture, defined as learned behaviors transmitted socially across generations, exists in whales and crows. Metacognition, the ability to think about one's own thinking, shows indications in rats and dolphins. The more diligently we investigate, the more apparent it becomes that the boundaries we draw between humans and other animals, between complex and simple minds, blur significantly under closer scrutiny. Part 11. The Celestial Stone Skimming Earth's Atmosphere. April 13th, 2029 will undoubtedly be a date etched in human memory, assuming humanity is still present to recall it. On this momentous day, asteroid 99942 Apophis, named after the ancient Egyptian deity representing chaos and darkness, will make a close pass by Earth at an altitude of 31,000 kilometers. For context, geostationary satellites orbit at approximately 35,000 kilometers. Apophis will traverse the orbital path of satellites crucial for weather forecasting, telecommunications, and GPS navigation. It will be visible to the naked eye, appearing as a point of light moving swiftly across the starfield. This event marks the first instance in recorded history where an asteroid of this magnitude will approach Earth so closely that casual observers can witness its passage. Current orbital calculations indicate no immediate threat of impact. The close approach is a certainty, its geometry well understood, but the trajectory will guide Apophis safely past our planet without any collision. This certainty is the result of decades of meticulous observation and orbital refinement. When Apophis was first discovered in 2004, initial trajectory calculations could not entirely dismiss a small but non-zero probability of impact during its 2029 passage. This announcement briefly alarmed the public and ignited intense scientific interest. Subsequent observations, as the asteroid appeared in different segments of its orbit, refined these calculations, progressively shrinking the uncertainty ellipse, the region where the asteroid could potentially be located at any given time, until the possibility of a 2029 impact was definitively ruled out. However, the narrative does not conclude in 2029. The close approach will significantly alter Apophis's orbit through gravitational interaction with Earth. When an asteroid passes in close proximity to a planet, tidal forces and gravitational acceleration invariably modify its trajectory, sometimes dramatically. The extent of this alteration depends on the proximity of the encounter and the relative velocities involved. Apophis will experience a substantial orbital deflection, modifying its orbital period around the Sun and consequently influencing its future potential for Earth crossings. Predictions for subsequent close approaches in 2036 and 2068 carry greater uncertainties because those future positions are contingent upon the precise details of the 2029 encounter, details that cannot be measured with absolute accuracy until the event itself transpires. The proximity of this passage, closer than geostationary orbit, presents an unprecedented scientific opportunity. Telescopes will continuously track Apophis as it approaches, meticulously measuring its rotational state, mapping its surface features, determining its composition through spectroscopic analysis, and ascertaining its size and shape via radar. The asteroid is approximately 370 meters in diameter, large enough to inflict regional devastation if it were to impact, yet small enough that discerning surface details from Earth-based observations remains challenging. The close pass brings it within the observational range of techniques typically reserved for near-Earth objects during even more intimate approaches. Radar astronomy will play a pivotal role. Radio telescopes, such as the Goldstone antenna in California and the Arecibo replacement facility, assuming its operational status by then, can bounce radio waves off the asteroid's surface and analyze the returning echoes. Radar provides exceptionally precise distance measurements, accurate to within meters, and rotation period measurements accurate to within seconds, along with surface roughness data that optical telescopes cannot match. Delay Doppler radar imaging generates two-dimensional representations where one axis signifies distance, determined by the echo's time delay, and the other represents velocity, derived from the echo's Doppler shift. These radar images reveal the object's shape, rotation, and surface topography, occasionally detecting boulders, craters, and ridges mere meters in size. Studies of rotation are crucial because asteroids spin, and their spin states offer insights into their history. Apophis rotates with a period of roughly 30 hours, a figure determined from light curve data illustrating variations in its brightness as different faces reflect sunlight towards Earth. This rotation rate is currently stable, but the 2029 Earth encounter is expected to alter it. Tidal forces exerted on the asteroid during its passage past Earth will exert torque on its rotation, potentially accelerating or decelerating it depending on the specific geometry. Measuring this rotational change will yield data regarding the asteroid's internal structure, indicating whether it is a solid monolith or a loosely aggregated rubble pile held together by gravitational forces. The Yarkovsky effect introduces an additional layer of complexity. Asteroids absorb solar radiation, warming their surfaces, and subsequently radiate this energy as infrared heat. This thermal radiation carries momentum, generating a subtle propulsive force that nudges the asteroid. For a rotating asteroid, the afternoon-facing side is warmer than the morning-facing side, and the asymmetric thermal emission produces a small but persistent force that either accelerates the asteroid's orbit or decelerates it, depending on whether its rotation is prograde or retrograde. Over millions of years, the Yarkovsky effect can significantly alter an asteroid's orbit, potentially shifting them from the main belt into Earth-crossing trajectories. For Apophis, the Yarkovsky effect must be measured with extreme precision to accurately predict its long-term orbital evolution. This effect is minute, causing orbital changes of only meters per year, but these incremental shifts accumulate over decades into kilometers of positional uncertainty. The 2029 close approach offers a unique opportunity to quantify the Yarkovsky acceleration by comparing the asteroid's actual observed position against predictions that do not account for thermal effects. Any discernible discrepancy will indicate the Yarkovsky influence and allow for the calibration of models used to forecast future encounters. Public perception presents both a challenge and an opportunity. Apophis has been featured repeatedly in news headlines since its discovery, typically accompanied by alarming language about killer asteroids and cosmic perils. The actual risk for any currently calculated encounter is exceedingly low, approaching negligible. However, communicating risk effectively is inherently difficult. Explaining that there is a 1 in 45,000 chance of impact in 2068 carries different meanings for different individuals. Statisticians interpret this as a negligible risk, far lower than countless risks we routinely accept. Yet for someone unfamiliar with probability, 1 in 45,000 can sound concerning, implying a genuine possibility rather than an event that is essentially impossible. Proposals for missions to Apophis have been circulating within the planetary defense community. Dispatching a spacecraft to rendezvous with the asteroid during or after its 2029 Earth encounter would provide close-up observational data that is unattainable from Earth. Such a mission could comprehensively characterize the asteroid's composition, internal structure, and surface properties in exquisite detail. This endeavor could also serve as a compelling demonstration of deflection strategies, employing methods such as kinetic impact or gravitational tugs to subtly adjust Apophis's orbital path and definitively prove our capacity to safeguard Earth from future celestial hazards. NASA's Double Asteroid Redirection Test, or DART, successfully collided with the asteroid Dimorphos in the year 2022, showcasing the efficacy of kinetic deflection precisely as anticipated. This impact demonstrably altered Dimorphos's orbit around its larger companion, Didymos, thereby establishing that humanity possesses the ability to modify asteroid trajectories with adequate foresight. The Apophis undertaking would build upon DART's groundbreaking achievement, testing deflection techniques on a celestial body of greater magnitude and potentially richer scientific intrigue. Anticipated conspiracy theories concerning NASA's alleged downplaying of impact probabilities are both predictable and baseless, though psychologically understandable. space agencies grapple with a delicate equilibrium between fostering open communication and averting public hysteria. Disseminating every preliminary orbital computation, complete with its inherent uncertainties, can inadvertently sow alarm when those uncertainties are substantial. Even though such wide variances are commonplace for newly detected celestial objects with limited observational data, withholding announcements until calculations are solidified, risks, accusations of concealment should an independent discovery occur or information be leaked. NASA and its counterparts have generally embraced a trajectory toward openness, publishing orbital projections and impact likelihoods through systems like Sentry and the Torino scale. Nevertheless, this transparency does not eradicate conspiracy narratives. It merely redirects their focus from concealing impacts to fabricating deflection failures or extraterrestrial involvement. The narrative framing of an asteroid that will merely graze Earth's proximity masterfully captures the dual essence of peril and wonder. These impending close encounters inspire awe. A PAUS poses no direct threat of collision, yet its passage will be sufficiently proximate for us to sense its presence, observe its transit, and witness the celestial mechanics that periodically convey mountain-sized rock formations into Earth's vicinity. This near miss serves as a poignant reminder that the cosmos is not an empty void. Remnants from the solar system's genesis continue their celestial ballet, occasionally intersecting with Earth's path. And while we have been remarkably fortunate thus far, such good fortune is not an immutable constant. Diligence is paramount. The capabilities for detection, tracking, characterization, and deflection collectively constitute humanity's safeguard against the cosmic lottery that, inevitably, will present an impact. This celestial event also presents a global educational opportunity. The defense of our planet necessitates international collaboration. Asteroids exhibit no regard for national boundaries, rendering a threat to one nation a threat to all. The United Nations Committee on the Peaceful Uses of Outer Space plays a vital role in coordinating global efforts to monitor near-Earth objects and develop responsive strategies. The approaching flyby of a PAUS in the year 2029 is poised to reignite interest in planetary defense funding and policy, potentially accelerating advancements in detection networks and deflection technologies. A glimpse toward the planetary procession of the year 2040 offers valuable context. The universe operates on timelines that disregard human temporal frameworks. Asteroids arrive as dictated by orbital mechanics. Planets align according to the fundamental principles of Kepler's laws. Comets descend from the Oort cloud, their trajectories dictated by gravitational disturbances initiated millennia ago. We meticulously record these occurrences on our calendars, anticipating them and preparing for them. Yet, their unfolding is governed by immutable physical laws, not human convenience. A PAUS will traverse our skies in 2029, irrespective of whether we are observing, whether we are concerned, or whether we are prepared. The universe's profound indifference to human affairs is simultaneously terrifying and liberating. Part 12. When the planets engage in a celestial dance, September the 20th, 2040. Mark this date on whatever calendar system endures the intervening years, for on this day, the solar system will present a geometric configuration so uncommon as to command attention, yet sufficiently prevalent for similar arrangements to recur with predictable regularity. 6 planets, Mercury, Venus, Mars, Jupiter, Saturn, and Uranus, will occupy a relatively constrained arc of the sky as viewed from Earth. Their longitudes, or angular positions along the ecliptic, differing by less than 90 degrees. The media will undoubtedly dub this a planetary alignment or parade, despite the technical inaccuracy of planets forming a perfectly straight line. They will, in essence, congregate within a singular sector of the celestial sphere, simultaneously observable from Earth's nocturnal hemisphere. This geometric phenomenon arises from the fact that planets orbit the Sun in roughly the same plane, known as the ecliptic, which is defined by Earth's orbital path. From our vantage point, planets appear to traverse a celestial route that mirrors the constellations of the zodiac. At times, planets are dispersed around the entire ecliptic, becoming visible at different moments as Earth rotates. On other occasions, their orbital positions converge, causing multiple planets to appear within the same sky region concurrently. These clustering events occur with a degree of regularity, albeit not with perfect periodicity. They are the consequence of planets possessing distinct orbital periods, which occasionally result in their positions aligning. The degree of rarity depends on the number of planets involved and the precision with which the alignment is defined. The convergence of all 8 planets within a 90-degree band transpires every few decades. Their confinement within a 30-degree span occurs every few centuries, achieving an actual linear arrangement where all planets exhibit 0-degree separation, as observed from the Sun, is highly improbable within human timescales, as orbital periods rarely synchronize into exact integer ratios that would facilitate perfectly recurring alignments. The celestial event of 2040 promises to be particularly conducive to observation, because the planetary cluster will encompass luminous planets visible to the naked eye: Mercury, Venus, Mars, Jupiter, and Saturn, all readily discernible without optical assistance, along with Uranus, which necessitates binoculars or modest telescopes. Neptune will be situated elsewhere in its orbit, not participating in this particular gathering. The planets will be observable in the evening sky shortly after sunset, rising in unison from the east and tracing an arc across the southern heavens, contingent upon the observer's latitude, affording hours of viewing opportunities. Amateur astronomers will find this an exceptionally rewarding occasion. Capturing all discernible planets within a single wide-angle photograph becomes feasible during these events, yielding images that vividly illustrate the architecture of our solar system. The varied luminosities and hues of the planets add considerable visual interest. Venus presents as a brilliant white. Mars is distinctly orange-red. Jupiter appears yellowish-white. Saturn shares a similar hue to Jupiter, but is somewhat less luminous. Uranus is barely visible as a pale blue-green disk, even through binoculars. Photographing them collectively results in a composite portrait of planetary diversity compressed into a single frame. Professional astronomers will also leverage these occasions for purposes extending beyond aesthetically pleasing imagery. Planetary alignments, contrary to persistent myths concerning tidal forces or seismic triggers, do not engender any extraordinary gravitational effects. However, they do provide valuable opportunities for simultaneous measurements across multiple planets using identical instrumentation and methodologies. Comparative planetology stands to benefit significantly from such opportune moments. The measurement of atmospheric characteristics of Venus, Jupiter, and Saturn within the same observational window serves to standardize instrumental and observational variables, thereby facilitating more reliable comparative analyses. Furthermore, the alignment might present possibilities for the detection of unusual celestial bodies. When planets converge, the background star field in that particular region receives heightened observational scrutiny. Faint asteroids, distant comets, or even undiscovered planets residing in the outer solar system could potentially be identified by observers scanning the area for planetary bodies. The hypothetical Planet 9, proposed as an explanation for the orbital clustering of distant trans-Neptunian objects, remains elusive despite dedicated searches. Its predicted location, should it exist, drifts gradually across the zodiac, and it is conceivable that it might be proximate to the region of planetary clustering in 2040, thus increasing the likelihood of its detection, simply because a greater number of telescopes will be focused in that direction. Mythological and cultural contexts have long been associated with planetary alignments throughout human history. Ancient astronomers meticulously charted planetary positions, noting conjunctions and alignments, and attributing significant meaning to these celestial occurrences. Astrological traditions, which persist despite a lack of scientific validation, ascribe meaning to planetary configurations based on symbolic interpretations and perceived correlations. The scientific worldview unequivocally rejects these associations, viewing them as instances of pattern recognition applied to random coincidences. Nevertheless, the innate human psychological response to celestial alignments remains potent. When planets convene in a particular sector of the sky, it evokes a sense of significance, even when one intellectually comprehends it as mere orbital geometry. Certain fringe communities will, without question, propagate predictions of catastrophic outcomes stemming from the 2040 alignment. The supposed capacity of planetary gravitational forces to induce earthquakes or meteorological calamities represents recurring doomsday scenarios entirely unsubstantiated by physics. The gravitational influence exerted by planets on Earth is inconsequential when contrasted with that of the Moon and the Sun. Even during planetary alignments, their cumulative gravitational pull induces negligible perturbations in Earth's orbit that have no measurable impact on geological or atmospheric processes. However, factual accuracy does not serve as a deterrent to speculation, and somewhere within the digital realm, an individual will assert that the alignment will precipitate disasters, and other individuals will lend credence to these pronouncements and make preparations. And when these predicted calamities fail to materialize, the predictions will be quietly relegated to oblivion or subjected to ad hoc rationalizations. Hidden scientific opportunities inherent in alignments include the precise determination of mass distribution within the solar system. The meticulous tracking of planetary positions enables rigorous testing of gravitational theories and the refinement of planetary mass estimations. Every planet exerts a gravitational influence on every other planet, engendering orbital perturbations that accumulate over extended periods. By meticulously measuring the current positions of planets and juxtaposing them with their predicted locations according to Newtonian gravity, astronomers can identify anomalies that might signify the presence of unknown masses elsewhere in the solar system, or, more speculatively, deviations from gravitational theory itself. The cultural dimension of alignments as global events holds considerable weight in an increasingly interconnected world. Unlike eclipses, which are observable only from specific geographical locales, planetary configurations are visible worldwide, weather permitting. This characteristic fosters shared experiences that transcend cultural and continental divides. In the year 2040, individuals in Tokyo, New York, Sydney, and Lagos will witness the identical planetary arrangement, creating a moment of cosmic solidarity that eclipses political and cultural distinctions. The analogy of a planetary choir serves effectively as a metaphor. Each planet navigates its own distinct tempo. Mercury, for instance, completes its orbit around the Sun in a mere 88 days, while Neptune embarks on a languid journey, requiring 165 years for a single revolution. These divergent orbital periods give rise to intricate rhythms and patterns over extended durations. When planets converge, it resembles a moment within a grand cosmic symphony where multiple instruments resonate simultaneously, forming a harmonious chord before diverging once more into individual melodies. While this metaphor should not be overextended, as planets do not literally produce sounds or create music, it effectively encapsulates the underlying principles of periodicity and pattern within orbital dynamics. The foreshadowing of the 2015 supermoon establishes narrative continuity. These alignment events and close celestial passages serve as markers of time in a manner that transcends individual human lifespans. An individual born in the year 2040 will be 12 years of age during the occurrence of the supermoon, 20 years old when Apus makes its close approach, and will have reached middle age before the advent of the subsequent significant planetary alignment. These cosmic phenomena function as reference points within collective generational memory, shared experiences that delineate epochs and impart structure to historical time beyond human constructs such as decades and centuries. Part 13. The Moon that Brushes Against Earth. November the 9th, 2022 will witness the closest lunar approach of the 21st century, a supermoon of such extraordinary magnitude that it stretches the very definition of the term. The Moon's orbit around Earth is not a perfect circle but an ellipse, meaning the Earth-Moon distance fluctuates between approximately 363,000 kilometers at perigee, its closest point, and roughly 405,000 kilometers at apogee, its farthest point. This variation in distance results in a corresponding fluctuation in the Moon's apparent size as observed from Earth. When the Moon reaches perigee during its full phase, presenting itself at its largest and most luminous, we designate it a supermoon. The supermoon of November 2020 will occur at an exceptionally close perigee, bringing the Moon to a distance of approximately 356,500 kilometers from Earth's center. This is about 3% closer than typical supermoons and roughly 6% closer than average full moons. While this difference in distance might seem insignificant in percentage terms, it is crucial to recall that we are comparing angular sizes, which exhibit a non-linear relationship with distance. A mere 6% reduction in distance translates to approximately a 13% increase in apparent diameter and about a 30% augmentation in perceived brightness. At this closest approach, the Moon will appear sufficiently large that the difference in size compared to average full moons will be readily discernible, even without optical aids. Place a photograph of the 2020 supermoon alongside one taken at an average lunar distance, and the disparity will be evident. The supermoon will occupy a greater portion of the sky, its features will appear magnified, and its brilliance will illuminate terrestrial landscapes with increased drama. Under optimal atmospheric conditions, with the Moon positioned near the horizon, the combined effect of its actual size increase and the moon illusion, a psychological phenomenon that causes moons near the horizon to appear larger than those overhead, will generate vistas that seem almost surreal. The photographic opportunities presented will be exceptional. Lunar photographers eagerly anticipate supermoons to capture the Moon in conjunction with terrestrial landmarks, leveraging its enhanced size to create dramatically composed images. The 2020 event will offer the ultimate opportunity for this generation of photographers. Preparations will commence years in advance, involving the scouting of locations from which the moon will rise or set behind interesting foreground subjects, and the precise calculation of timing and positioning to achieve the desired shot. The augmented brightness carries implications extending beyond mere aesthetics. Moonlight, in general, possesses sufficient intensity to cast shadows and influence the behavior of nocturnal fauna. Supermoon light is even more potent, capable of producing distinct shadows from objects and illuminating landscapes to levels approaching those of twilight. Nocturnal creatures that regulate their activities based on lunar phases may exhibit responses to the unprecedented brilliance. Predators relying on vision for hunting might gain an advantage over prey species that depend on darkness for concealment. Conversely, prey animals might modify their behavior, opting to remain concealed during the peak hours of illumination. Extreme tidal surges represent the most significant physical consequence associated with close lunar approaches. Ocean tides are a result of gravitational gradients, the disparity in the moon's gravitational pull on the near side of Earth compared to its far side. This gradient engenders two tidal bulges, one oriented towards the moon and another diametrically opposite. Earth's rotation then carries coastlines through these bulges, giving rise to the familiar twice-daily tidal cycle. The intensity of these tides is directly proportional to the moon's distance, with closer moons generating stronger gradients and consequently higher tides. Spring tides, the periods of highest tides occurring during new and full moons when the sun and moon are in alignment, will be amplified during the 2020 supermoon. Coastal regions already contending with elevated spring tides will experience water levels several centimeters higher than usual. While this increment might not appear dramatic, during high tide coinciding with storms, those additional centimeters can be the decisive factor between water remaining within its channels and overtopping sea walls, leading to the inundation of coastal infrastructure. Coastal flood advisories will likely be issued for vulnerable areas, particularly those already confronting rising sea levels attributed to climate change. Speculation regarding seismic coupling ventures into less certain territory. Certain researchers have investigated statistical correlations between lunar phases and tidal forces in relation to earthquake occurrences, seeking evidence that tidal stress on fault lines might precipitate earthquakes that are already on the verge of rupture. The prevailing scientific consensus posits that any such effect, if indeed it exists, is of negligibly small magnitude. Faults rupture when accumulated tectonic stress surpasses the frictional forces holding them in place. Tidal stresses are orders of magnitude weaker than tectonic stresses. However, for fault lines situated at the very precipice of failure, even minor additional stresses could theoretically provide the impetus for rupture. Studies have identified weak correlations between tidal forces and earthquakes in specific fault systems, but not in others, with effects so minute that they are difficult to distinguish from statistical noise. The 2020 supermoon will serve as a natural experiment. If tidal triggering is a tangible and measurable phenomenon, we might anticipate a slightly elevated global earthquake rate in the days surrounding its closest approach. If the rates remain within normal parameters, it will further bolster the conclusion that tidal influences on seismicity are inconsequential. The cultural reception of the supermoon will likely encompass both celebration and apprehension. Festivals and public viewing events will draw substantial crowds to locations offering clear, dark skies and iconic landmarks. Lunar eclipses, when they coincide with supermoons, transform into media spectacles, captivating millions of viewers. Even in the absence of an eclipse, the record-breaking nature of the 2020 event is bound to generate considerable interest. Concurrently, various doomsday prophecies and apocalyptic interpretations will proliferate online, asserting that this proximate celestial encounter portends dire calamities. These predictions adhere to predictable patterns and will be equally predictably incorrect, yet they will momentarily capture attention and engender undue anxiety among individuals unfamiliar with astronomical realities. The expression, "the night that glowed like day," represents a hyperbolic exaggeration, yet it effectively conveys the qualitative experience of exceptionally bright moonlight. The human eye possesses remarkable adaptability to darkness, with pupils dilating to capture more light and photoreceptor cells enhancing their sensitivity. Under conditions of complete dark adaptation, the range of sensitivity in human vision spans numerous orders of magnitude. Moonlight during a typical full moon provides ample illumination for comfortable navigation, reading large print, and discerning colors in a rudimentary fashion. Supermoon illumination intensifies this further, potentially enabling the reading of standard print and the perception of colors with greater vividness. In conjunction with exceptionally clear atmospheric conditions and a dark surroundings, the experience approximates the illumination levels experienced during deep twilight. Studies pertaining to atmospheric scattering benefit from the presence of bright moonlight, as lunar illumination offers a stable light source for gauging atmospheric properties. Research teams investigating aerosols, clouds, and atmospheric chemistry occasionally utilize moonlight as a calibration standard or to extend observational periods beyond daylight hours. The supermoon provides an unusually high signal level, potentially facilitating more precise measurements or the detection of subtle effects that typically fall below the threshold of detection. Citizen science initiatives could orchestrate global observations of the supermoon, gathering data on apparent brightness, color, and atmospheric phenomena from participants worldwide. Similar projects have successfully amassed observations of eclipses, meteor showers, and auroras, thereby compiling data sets that complement professional observations and foster public engagement with astronomy. The supermoon presents an accessible celestial target that anyone can observe and photograph, effectively lowering the barriers to participation. The transition to discussing comets that might surpass even this supermoon in brilliance serves to set up the concluding narrative points. The moon, at its closest approach, will be truly spectacular, yet it represents a recurring phenomenon, the most luminous in a continuous sequence of supermoons that occur monthly to varying degrees. Comets, conversely, represent unpredictable wildcards, occasional visitors that can rival or even exceed the moon's brightness, but they do so infrequently and without any dependable schedule. This comparison effectively highlights the distinct natures of these celestial phenomena. The predictable, cyclical movements of bodies bound by regular orbits versus the chaotic, punctuated appearances of comets descending from the outer darkness. Part 14. 2060, the most luminous comet ever. In the year 2060, an event is anticipated that no living human being has ever witnessed. The predictive forecasts are already established. The orbital calculations have been completed. Astronomers are marking their calendars for an event that will eclipse anything in recorded history. A colossal object originating from the Oort cloud, that distant reservoir of comets encircling our solar system, is hurtling towards the inner solar system on a path that will bring it sufficiently close to the sun to become truly spectacular. It won't just be bright, nor merely visible, but potentially as luminous as the moon itself, commanding the night sky for weeks, or perhaps even months. If current projections prove accurate, This celestial visitor will be the astronomical highlight of the century. It promises to be a once-in-a-lifetime spectacle, discernible even in daylight, capable of casting discernible shadows at night, and fundamentally altering humanity's perception of the heavens for all who witness it. To contextualize this, most comets traversing the inner solar system are faint, requiring optical aids like binoculars or telescopes for observation. A select few each decade achieve naked-eye visibility, appearing as diffuse patches of light with modest tails. Approximately every few decades, a brilliant comet emerges, one that garners significant media attention and compels people to venture outdoors to gaze upwards. Comet Hale-Bopp in 1997 was one such instance, remaining visible for over 18 months and bright enough to be easily observed from urban areas, even with light pollution. Prior to that, Comet West in 1976 offered a stunning display for those who awakened before dawn to behold it. And of course, there is Halley's Comet, which reappears every 75 to 76 years and has been documented by humankind for over 2,000 years, appearing in Babylonian records, Chinese chronicles, and the Bayeux Tapestry. However, even Halley's Comet, at its most brilliant, is merely a bright comet. It is undoubtedly impressive, but it does not dominate the celestial sphere. The 2060 comet, should it fulfill its potential, will achieve precisely that. Current models indicate it could attain an apparent magnitude of -10 or even -12, rendering it as brilliant as a half-moon or potentially a full moon. To comprehend this, one must understand that the magnitude scale is logarithmic and operates in reverse. The Sun possesses an apparent magnitude of -26.7. The full moon is at -2.7. Venus at its brightest is approximately -4.9. A bright comet like Hale-Bopp peaked at around -1. Each incremental step signifies roughly 2.5 times more light. Therefore, a magnitude 10 comet is not merely twice as luminous as Hale-Bopp. It is thousands of times brighter. What accounts for a comet of such magnificence? Size is a critical factor. Unquestionably, the nucleus of the 2060 comet is estimated to be extraordinarily large, possibly ranging from 50 to 100 kilometers in diameter, positioning it among the most substantial objects ever to journey into the inner solar system from the Oort cloud. For comparative purposes, the nucleus of Comet Hale-Bopp was approximately 60 kilometers across, which was already considered substantial. However, size alone is insufficient. The comet must also approach the Sun closely, close enough for solar heating to vaporize immense quantities of ice, thereby generating a coma that could expand to a size larger than Jupiter and a tail extending for hundreds of millions of kilometers. The 2060 comet satisfies all these criteria. Its perihelion will bring it within approximately 0.3 astronomical units, roughly 45 million kilometers, placing it within Mercury's orbital path. At such proximity, the Sun's heat will vaporize not only water ice, but also more volatile compounds such as carbon monoxide and carbon dioxide. Yet, beyond the scientific intricacies, something more profound is unfolding. For a fleeting moment in 2060, humanity will share a unified experience. Individuals across every nation and continent will direct their gaze upwards to witness the same phenomenon, a comet so resplendent that it cannot be overlooked, so awe-inspiring that it transcends linguistic, cultural, and political divides. The 2060 comet will be impossible to ignore. It will dominate the twilight and nighttime sky, visible even from brightly illuminated cities, emitting sufficient light to read by in darker locales. And this is where matters become intriguing and perhaps a touch unsettling. What transpires when a light source is introduced into the night sky that rivals the moon? We are aware that moonlight influences ecosystems. Nocturnal creatures modify their behavior based on lunar phases. Predators hunt differently during full moons. Human circadian rhythms, the internal biological clocks governing our sleep-wake cycles, are affected by ambient light levels. Throughout the entirety of human existence, the moon has been the most luminous object in the nocturnal sky. What will be the consequence of introducing a third variable into that equation? The truth is, we do not know. The comet will remain visible for weeks, potentially months, and during this period, it will be infusing the nighttime environment with light at levels Earth has not experienced from a comet in recorded history. Now, let us consider the less favorable possibilities. Whenever a comet ventures this close to Earth, apprehension regarding impacts and catastrophes inevitably arises. Let me be unequivocal. The 2060 comet will not collide with Earth. Its orbital path is meticulously characterized, and it will pass us by millions of kilometers. However, this does not render it entirely benign. Comets shed material as they approach the Sun. Dust, minute particles, and occasionally larger fragments detach and disperse along the comet's trajectory. Should Earth's orbit intersect the comet's path after the comet has passed, we could encounter this debris stream, precipitating a spectacular meteor shower. But a more concerning, albeit unlikely scenario exists. Comets occasionally fragment as they approach the Sun. Thermal stress, tidal forces, and outgassing pressure can all contribute to structural failure within a comet's nucleus. If the 2060 comet were to fragment, and if one of those fragments were to possess an orbit that brought it closer to Earth than anticipated, we would face a significant issue. The probability is exceptionally low, yet not impossible. This underscores the critical importance of asteroid and comet tracking initiatives. Nevertheless, one hopes that the predominant reaction will be one of profound wonder, because, irrespective of any other factor, the 2060 comet will be breathtakingly beautiful. It will serve as a potent reminder that we inhabit a universe capable of producing phenomena of extraordinary magnificence. For a duration of several weeks or months, conversations at the dinner table will invariably involve discussions of tail structures and coma dynamics. Children will prolong their wakefulness to observe the comet. It will become an integral part of the cultural tapestry of that generation. And when it has concluded its celestial journey, when the comet has completed its orbital swing around the Sun and commences its retreat towards the outer solar system, we will be left with photographic records and cherished memories. Yet, even as it recedes, another date on the cosmic calendar signifies an equally profound milestone. Part 15, 2177, Pluto's inaugural birthday and a cosmic contemplation. On February 18, 1930, a young astronomer named Clyde Tombaugh was meticulously examining photographic plates at the Lowell Observatory in Flagstaff, Arizona. He was engaged in a search for a hypothesized ninth planet, a celestial body situated beyond Neptune, which might account for subtle anomalies in the orbital patterns of the outer planets. The task was arduous, involving the comparison of photographic pairs taken days apart with the objective of identifying any celestial object that shifted position against the backdrop of fixed stars. And then he discovered it, a minute point of light that had moved between exposures. Planet X, the ninth planet, Pluto. The discovery garnered worldwide headlines. Pluto was the first planet identified by an American, and it captured the public imagination in a manner rarely seen with astronomical discoveries. The name Pluto, suggested by an 11-year-old girl in England named Venetia Burney, seemed remarkably fitting. The god of the underworld for a distant, dim world at the periphery of the solar system. For 76 years, school children were taught that the solar system comprised 9 planets, and Pluto, diminutive and enigmatic, was considered the final frontier before the vast darkness of interstellar space. Then, in 2006, the International Astronomical Union revised the definition of a planet. Pluto satisfied 2 of the 3 criteria, but failed the third. It had not cleared its orbital path of other celestial debris. Under the revised classification, Pluto was redesignated a dwarf planet, and the solar system was thereafter recognized as having 8 planets. This demotion elicited a surprisingly strong public outcry. People had developed an affection for Pluto, this distant, underdog world. However, consider this perspective. In 2177, exactly 247 years after its discovery, Pluto will complete precisely 1 full orbit around the Sun. It will return to the identical spatial position where Clyde Tombaugh first observed it on those photographic plates. Reflect upon the implications of this. Pluto's year, the duration required to complete a single orbit, spans 247.9 Earth years. When Pluto was discovered in 1930, it had completed approximately 36% of one orbit since the signing of the Declaration of Independence. We discovered Pluto, studied it, dispatched a spacecraft for a flyby in 2015, witnessed its reclassification, and engaged in extensive debate and argument. And throughout all these developments, Pluto had not even completed a single revolution around the Sun. This offers a profound lesson in temporal scales. We humans typically live, at best, for 80 to 100 years. This represents the span of direct memory and lived experience for any individual. Our civilizations persist for longer durations, with continuous written records extending back approximately 5,000 years. Yet, even on this scale, Pluto has completed merely about 20 orbits. The entire epoch of human civilization encompasses merely 20 circuits around the Sun for this distant world. And if we broaden our perspective to the 4.5 billion year history of the solar system, Pluto has completed roughly 18 million orbits. This figure might seem substantial, until one recognizes that Earth has completed 4.5 billion orbits within the same time frame. But it is not solely Pluto. The outer solar system operates on temporal scales that dwarf human experience. Neptune requires 165 years to orbit the Sun. Since its discovery in 1846, Neptune has completed little more than a single orbit. Uranus takes 84 years. Saturn requires 29 years. These are worlds that traverse the zodiac at a stately, almost imperceptible pace. Ancient astrologers recognized only 5 planets beyond Earth, because these were the only ones whose movements across the sky were readily discernible within a human lifetime. This raises an intriguing question. What is the maximal temporal scale that humans can genuinely comprehend? We can intellectually grasp that the universe is 13.8 billion years old, that the Sun formed 4.5 billion years ago. We can recite these figures, incorporate them into textbooks, and impart them to students. But do we truly internalize them? Can any human mind truly hold 13 billion years of time within its cognitive framework in a manner that feels tangible? Likely not. Our innate intuition is calibrated to human lifespans, to the duration we anticipate living. Beyond a few generations, time becomes an abstract concept. This is precisely why Pluto's inaugural birthday since its discovery serves as such a poignant marker. It represents a temporal scale that is only just within the grasp of our civilization's comprehension. 247 years spans from 1777 to 2177, encompassing over a century and a half into our future. This duration exceeds any human life, outlasts most institutional existences, yet remains sufficiently concise to allow for the tracing of cultural continuity. Individuals in 2177 will be able to refer back to records pertaining to Pluto's discovery and comprehend the endeavours of those astronomers and their significance. However, when Pluto completes that initial orbit in 2177, it will merely be commencing its second orbit since its discovery, and that second orbit will extend for another 247 years. Pluto will not complete a third orbit until 2671. The individuals who will witness Pluto's second birthday have yet to be born and will not come into existence for centuries. And by that time, will humanity still hold Pluto in regard? Will we continue to observe the heavens, meticulously track the planets, and commemorate these cosmic milestones? I would like to believe that we will. Despite all adversities, despite the pervasive chaos that often characterizes human conduct, we have maintained astronomical observatories for centuries. We have diligently preserved records, transmitted knowledge across generations, and built upon the discoveries of our predecessors. The very fact that we can accurately calculate Pluto's orbit and predict its position in 2177 stands as a testament to the power of accumulated knowledge, a testament to humanity working collaboratively across generational divides towards shared objectives. And speaking of extensive temporal scales, consider this. When 3I Atlas entered our solar system in 2024, it had been traversing interstellar space for millennia. If it originated from a star system 10 light-years distant, travelling at 66 kilometers per second, it would have required approximately 45,000 years to cover that expanse. Throughout that entire period, this comet remained frozen, unaltered, drifting through the cosmic void. Subsequently, it spent a mere few months within our solar system, was disintegrated by the sun, and then vanished. However, comprehension differs from lived experience. We can precisely calculate Pluto's orbital path, but we cannot truly feel the sensation of taking 247 years to complete a solar circuit. We can accurately measure the sun's lifespan as 10 billion years, yet we are incapable of viscerally grasping such a temporal magnitude. We are inherently constrained by our biology, our mortality, and our position within the fabric of space and time. When Clyde Tombaugh discovered Pluto in 1930, he was 24 years of age. He passed away in 1997 at the age of 90, having lived to witness spacecraft visit every planet in the solar system and humans set foot on the moon. Yet, he never had the opportunity to see Pluto complete a single orbit. No human alive at the time of Pluto's discovery will survive to witness its inaugural birthday. That milestone will belong to individuals yet to be born.